Okay, good afternoon, everybody. We'll resume our lecture series now. Our next speaker is Professor Bengt Johansson. He's been at KAUST for more than 2.5 years now. And prior to that, he had spent his whole life in Lund, Sweden. So he got his PhD at Lund University in Sweden, and soon after graduating became a junior professor and eventually a full professor. And he always likes to be referred to as a professor of internal combustion engines. And that's really what he is an expert in.
That I am, yes.
Yeah. And fortunately, it took, I think many people tried to pull him away from Sweden, but finally KAUST was successful a few years ago in getting him to come here, where now he leads the internal combustion engine research here in the Clean Combustion Research Center. He has a lot of years of experience in the field, has chaired many committees and sessions at the Society of Automotive Engineers, organized some of the leading thinkers in the field to come together, having industry and academics partner together to develop new types of combustion concepts. He's a world-renowned expert in low-temperature combustion or homogeneous charge compression ignition. And more recently, I'm sure we might hear sometime during this lecture, is the development of very high-efficiency engine concepts. So please welcome Professor Bengt Johansson.
Thank you. So, low temperature combustion, HCCI. This is not the first time I'm giving this type of lecture. I do remember one invitation from India. It was like 10, 15 years ago. I just got an invitation, and of course I didn't read the email. I just said, yes, sure, why not? And then when it was time to move to India, I looked at the actual invitation, and I realized that this invited talk was for 5 hours. First day. Second day, it was 6 hours, and there was also a third day. So, oops, time to make a slightly longer talk than normal. So this 4-hour talk is actually the shortened version, right? So low temperature combustion was that. Well, the basic idea is not to burn too much. And that means that the efficiency actually goes up because temperature is not too high, meaning less heat losses. The extreme is to burn nothing. And burning nothing is possibly the best possible way to reduce emissions, right? There will be no CO2, there will be no unburned hydrocarbon, there will be no nitric oxides, no particulates, nothing. That's really good, right? The only problem is that if you burn nothing, you get nothing out, meaning there is no output power. And that's then a little bit of a problem. The efficiency, how do you define efficiency? We get nothing. So, low temperature combustion is all about improving the thermodynamics, improving the combustion process as such. But we should not forget that if we burn nothing, we get nothing. So there is a trade-off. A regular combustion concept, you burn a lot, meaning you get a lot of power output, and by that you also get the very high mechanical efficiency. So there's a big trade-off between the internal efficiency in the engine. I will talk about that more in detail eventually. But even so, there is a big difference comparing just the cycle and the actual complete machine. And we shouldn't forget that. It's very hard to do both, but you should. Okay, so what's HCCI? Well, it's not this. So once upon a time, we had the spark ignition engine to the left. It's a picture stolen from the Haywood textbook. So you have a spark plug, you have a flame propagating, and once the flame hits the back wall, we're done. And let's make sure that it really hits the back wall, and so we don't have auto ignition. It is unburnt end gas. So that's kind of it. We need to model the turbulent flame propagation, and that, of course, depends on a lot of things. But we should also stay away from the bulk auto ignition, the NOC. The very big advantage with this one is that we can operate stoichiometric. Operating stoichiometric means that the freeway catalyst can be there, and that means there will be negative emissions, meaning below zero. And there's actually some indications that in the range of 1/3, 1/4, in that range, of all cars with a gasoline engine would have negative emissions today. So a car out there is actually cleaning the air. The problem with SI is that the efficiency is a little bit so-so. We control the load by reducing inlet pressure, getting a lot of pumping losses. We're limited with knock. Compression ratio needs to be low. And that's not very good. So very, very clean, this one, but not very efficient. And the conventional diesel is kind of the opposite. Quite efficient, but severe problems with the NOx and soot. So the aim of the game is to, well, get both in the same machine. That means HCCI. So we can get the high efficiency of the diesel cycle. We can even beat the diesel. We can get extremely low NOx levels, no particulates generated from combustion. But there is a significant problem with combustion control power density. So that's going to be most of my talk. HCCI was that. How do we tame it? And what is happening if we do not tame it? It's really an unstable combustion process. If you do uncontrolled HCCI experiments, the lifetime of the engine is normally 2 seconds, or maybe less. So it needs to be closed-loop controlled. Otherwise, it's not working. The other two bubbles here, spark-assisted compression ignition, SACI, as well as partially premixed combustion, PPC. I think the SACI I will use one slide to show that we should stay away. Interestingly enough, that's what Mazda is using to put HCCI in production. But I will not talk too much about that today. PPC, though, that's kind of halfway back from HCCI towards the diesel process. And I will spend roughly half the time on this PPC. It's not as low NOx as HCCI. It's maybe 10 ppm instead of 1. The diesel engine, however, is like 100 to 1,000. So it's still very much less. So what's HCCI? Well, it's kind of simple. You mix fuel and air, and you do that before combustion, as in a spark ignition engine. And then it auto-ignites. Once you reach the correct temperature, off it goes. That's simple, right? Okay, so that means the rest of the afternoon is kind of no need. Go on a snorkeling trip or something instead. Not really. There are some additional things that you need to know. So this is the outline, basics. Done some engine studies, laser diagnostics, modeling, closed-loop control, fuel effects, and possibly some summary. And that's then the HCCI part. So what's this? This is a slide taken from a SE paper from 1979 from Onishi, Japanese. He generated possibly one of the best papers I've seen ever, starting with presenting a new combustion concept, showing some engine results, some optical diagnostics, and then he ended the paper with saying, yeah, by the way, I also put it in production. That's good enough, I guess. So what's here on the slide? Well, if you look to the left, that's conventional spark ignition combustion. So what's on the axis? Well, Q here is the amount of heat per mass unit, and the W here is mass. So we have two distinct zones. We have a burnt zone, unburnt zone, and we have this reaction zone in between, called a flame. And we see that it takes some time to release all the heat. So capital Q here is the integral from 0 to W1, Q dW. So we integrate from left to right. And that takes some time. So locally, reactions are fast. but the reaction front takes some time to get moving. So here to the right, it's what Onishi called active thermo-atmospheric combustion, ATAC. That's, by the way, what we called HCCI back in Lund the first 5-6 years before deciding on using the HCCI term. So, oops, wrong way. So here it's the same amount of heat, capital Q, integrating from 0 to Q1 W dQ. So we integrate from bottom to top, and this tells us that things are happening all over the place. So it's a distributed reaction. So no flame propagating through the combustion chamber. It's a distributed reaction. Chemistry is slow. It needs to be slow, otherwise all the heat is going to be released at one instant of time. And that's not an effective way to operate an engine. Trust me. Tried it. So for chemistry to be slow, we need to dilute. We need to have much more air, much more residual gas, much more something else that absorbs heat from the chemical reactions. Slowing down chemistry by adding more mass. You can see that Onishi did not draw a horizontal line. There is a slope here. So it's enough. Maybe I should activate this. It's enough of a slope to show that in some parts of the cylinder, more things are happening than in other parts of the cylinder. So it's not completely the same all over the place. Some parts would react a little bit faster because temperatures may be a little bit higher, a little bit richer mixture, or something is promoting reaction rate there. But it's not really exactly here or there. It could be some opposite location, some other cycle. But Onishi drew not horizontal line to indicate it's not a fully distributed reaction. So, same amount of heat released, capital Q. Two ways to do it, either having a fast flame, but still taking some time to progress through the volume, or a distributed reaction with slow chemistry. So that's kind of it. So we saw this paper from 1979 who said, yeah, right, but is that really what's happening? So we took this two-stroke engine. It's for a chainsaw. We replaced the cylinder head up here with a window, so we can see from the top here with a high-speed camera. Actually, not high-speed camera, just a camera taking a picture per cycle. So there are two spark plugs, one up here and one down there, and you can see the two flames. So this at the 9,000 RPM, and that's when we operated the engine with the normal fuel, actually isooctane. Then we swapped to regular gasoline to flush the carburetor at the end of our experiments. And to our surprise, the engine swapped combustion mode to HCCI, and it revved up to 17,000 RPM. So the picture to the left is slightly before TDC, and the one to the right is close to TDC. We can see distributed reactions, not a homogeneous signal, but very distributed. More homogeneous a little bit earlier in the cycle, but anyway. It seems to be about right what Onishi told us. This also told us that there is not really an upper speed limit for HCCI. Some people claim that, but it's not true. So this is a normal flame propagation. It starts in the center, and then the flame propagates, and once it reaches the back wall, we're done. You can see most of the heat release is actually happening very late when we don't see much through the window. So this is a window in the piston. And let's see if we can get the HCCI stuff working. Then nothing happens, because it wouldn't need to happen until it's close to TDC. You might see the number up there in the corner up there. And now it's about time to get started. And you see it starts in one end of the combustion chamber, kind of do a loop, and burning it a bit slower, actually, in the core of the combustion chamber. But distributed reactions seems to be the case. So, what do we need to run HCCI? Well, we need temperature high enough to get combustion going, and then we need enough dilution. So once combustion gets going, it shouldn't blow up the engine. That's pretty much it. Quite simple, actually. So what temperature is needed to get it going? Well, that depends on the fuel. What I'm showing here is the ignition temperature as evaluated from pressure trace. And 4 different fuels. If we start with the isooctane here, we see that it's around 1,000 Kelvin, and then it goes. Shown also is the equivalence ratio, or actually lambda, that is possible when operating HCCI. So lambda is 1 over equivalence ratio. So 2.5 as the rich limit, that's extremely lean. And the lean limit is then 4, that's even more lean. So around 1,000 Kelvin, and not much happening as we lean out. A little bit higher temperature needed, but not much. Natural gas, having a higher octane number, also needing a higher temperature to get going. Here we are up at 1150 or so, a little bit of a slope, but not much with equivalence ratio. And then we see that it's a bit interesting. The alcohols, ethanol and methanol, they would have a higher octane number than 100, but still needing less ignition temperature. So there is a link between HCCI behavior, octane number, but not a perfect one-to-one correlation. So some fuels behave a little bit outside the correlation, especially alcohols. Okay, so the temperature here is evaluated from measuring the pressure trace and then taking it 1 degree crank angle before 1% heat released. So this is the amount of heat released. So just using the pressure trace to get the temperature. So rich limit, lean limit. The rich limit is when we start to burn really fast. And here is shown this rich limit. It's in the range 2.5 or so, depending on how you operate the machine. And actually, if you would take 1 more data point, it would be way up above the scale. It starts to go really bad. So this is the pressure rise rate. How fast do we burn the fuel? And that's associated with noise. The higher your pressure rise rate, the more noise from the machine. The peak pressure rise rate measured so far is 70. Why not measuring more than that? It's because the pressure sensor can't respond faster. But then again, it's noisy enough. At the other end here is CO, and that's the lean limit. If you burn too lean, the temperature increase due to combustion is not sufficient to fully oxidize CO. So actually, this is stopping at 4.5 or so in lambda. We did lambda 14, and at lambda 14, there is absolutely no CO2 in the exhaust. So you go from fuel to CO, but there is not enough to go from CO to CO2. So I did present those results to well, some Swedish government agency. And they said, ooh, this is a CO2-free combustion engine. There is absolutely no CO2 in the exhaust. So what did I reply? Anyone? Yes, give me the money. Actually, I didn't. It was kind of stupid. But I said, okay, there is no CO2, but it's a lot of CO, and the CO might oxidize the CO2 in the atmosphere anyway. Okay, the other end, if you burn too much fuel, temperature goes up, and that means you start to form NOx. Thermal NOx, well, you can see it here, is in the range of a couple of ppm if you go low enough peak temperature. So the temperature shown here on the x-axis is evaluated from the pressure trace again, and is assuming a homogeneous temperature in the cylinder, which is not quite true. So NOx levels of 0 to 2 ppm, that's extremely low. SI would be in the range of 1,000, couple of thousand. Diesel, about the same level. So this would be some 3 orders of magnitude less than a conventional machine. But showing numbers like this is not something you should ever do, because no one can actually relate to it. I will show how to present it in a few slides to actually get some attention. So, the 3 temperatures of HCCI, this is the take-home message. I'm putting it kind of early in the talk because soon enough the lunch cannot kick in. But before that, what you need to know is that combustion starts at 1,000 Kelvin. You need to reach 1,500, otherwise CO is not going to CO2. And you should stay away from NOx formation, and that means stay below 2,000. So that's round, even, nice numbers. Start at 1,000, make sure you reach 1,500, don't go above 2,000. So that means the temperature increase due to combustion needs to be 500, shouldn't be more than 1,000, and that's a ratio of 2 to 1. So that also tells us do not try to operate HCCI with a very, very, very wide range of equivalence ratios. Temperature increase is directly proportional to equivalence ratio. The more fuel you burn, the higher the temperature of the combustion. So it is a 2 to 1 ratio, and you cannot expect to get good results if you make it much wider. I've seen hundreds or possibly thousands of papers on HCCI not understanding this. So I said 2 to 1, and if you look at the red arrows from 2 to 4 in lambda, or 2.5 to 5, it seems to be about right. So HCCI, why do it? This is the emission spectra from a normal diesel engine. So this is particulate matter, and then you have NOx. This is, well, a little bit old now, from 2002, but anyway, this is the normal trade-off you have with a diesel engine. Either you go high soot, low NOx, or high NOx, low soot. If you're lucky, you can find a corner here that would be within the emission compliance zone. So this is Euro 3 from 2000, so yeah, you could do it without too much of a problem. If you want to reduce particulates, you need to use a particulate filter. If you want to reduce NOx, you need to use SCR. And then you need to be here in this 0.0 point. And actually, if you zoom in twice, the green point here is HCCI without after treatment. So no SCR needed, no DPF needed. That generated a little bit of interest when HCCI was new. So we can do a really clean emissions, and then how about efficiency? If we want to operate our engine at part load, how should we do it to maximize efficiency? Well, we should burn fast at the TDC. That's the ideal Otto cycle. It should be very lean. That's also good for the thermodynamic cycle, because the gamma, or ratio of Cp over Cv, would be high. We should have a high compression ratio, and we should operate very, very lean so we don't have any pumping losses. So we're doing all that with HCCI, so it's all good. So some of the first papers on HCCI, this is from 1992. It's from the German magazine MTZ. Of course, you need to read it in German, or possibly get the English translation, but even so. They took a 1.6 liter Volkswagen engine and converted it to HCCI. So it's a complete machine, multi-cylinder, and they got these numbers here with the arrows slightly off, but anyway, what you see here is the lower line would be a conventional spark ignition engine, stoichiometric, and we see that, well, this is load in BMAP, very low load, like 2.5 or so here, and well, actually, these arrows should be here. at 1.5. So I normally pick the 1.5 point because here you have 15% efficiency with a conventional machine, and you have 30% with HCCI. So that means it's a factor of 2 in efficiency, or 100% improvement, big numbers. Why did I normally pick the 1.5 bar? It's because that's where you get the maximum benefit. Brake efficiency is 0 by 0 bar by definition, and as you go up in load, you will see that it's getting less of a difference. The conventional machine is getting reasonably okay. We talk about something like 30% efficiency at really low load, so that's good. This is from 2002, so it's a decade younger, and the black line here is a conventional SI machine, and the blue is HCCI. And here we're talking about the 50% reduction in net specific fuel consumption. So it's not including the friction losses, but still. So, seems to be good. This controlled auto-ignition thing, I will talk about that in due course. And these will be some results from Lund, comparing 3 different multi-cylinder machines running SI in green. This is SI with a high compression ratio, and then the black is the same machine again, but in HCCI mode. So rough numbers, you go from 30 to 40 to 50% by doing these modifications. And the 50% thermodynamic efficiency is quite good, and maybe possible in real life. So the summary of HCCI at this level, why should we do it? Well, we get very high efficiency and we get very low emissions. And depending on who you talk to, it would then be for different reasons you would do it. If you talk to people using SI engines normally, they would not be interested in lower emissions because the freeway catalyst is really cleaning everything. They're only interested in efficiency. If you talk to diesel persons, they have a big problem with the SCR, DPF actually working very good. Low emissions would really be of interest. So depending on who you ask, there will be different benefits. But it's kind of the best of both in one machine. Oh, animation, question mark. Let's see if that works. And this is an animation of HCCI. Let's do it like this. So this is showing that the piston goes up and down, and the valves open and close, and eventually you do a cycle. What you have here would be 5 different sliders that would affect HCCI combustion. And output, there is a pressure trace, and there will be some power, efficiency, emissions, and maximum pressure as the output from the cycle. So this animation is kind of the rate you get results if you do DT power type of simulations, meaning 1D simulations. I'm pretty sure Hong did not show real-time simulations before lunch. Did you? Nope. I take that as a nope. So if we click on the red button and make it blue, it's now real-time. And it means that this is pretty much a virtual HCCI engine. And what we're doing now is to set the different parameters that affect the HCCI combustion, so combustion starts earlier or later in the cycle. So what we have here is pretty much a timeline from -30 to +60, and this is then the top dead position. So the pressure goes up due to piston motion. Here's the combustion and the expansion then. And currently, the power is 150 or so kilowatt, 35% brake efficiency, onboard hydrocarbon and CO, well, reasonably low, no NOx, 0 ppm, and this is the peak pressure. So you think this is a simulation, but it's not really, because this is a compilation of experimental data. So we measured everything as a function of everything, pretty much. And then we have the response from each and every variable, and also the cross correlations between those. So how about the sliders? Well, this is fuel-air ratio. What's going to happen if I add more fuel? Well, if I add more fuel like this, it's starting to make noise. And that's because combustion is now too fast, too violent, and we're starting to get pressure oscillations, kind of similar as engine knock. We also see that the combustion is quite early. It starts to burn before TDC. That means that the pressure increase here before TDC is actually a negative work. That's not very good. So that's not something we want. So how about adjusting inlet temperature? How should we adjust this to get combustion burning later in the cycle? Well, of course, we should reduce it, right? So if we reduce inlet temperature like this, it's quiet. This is kind of when people wake up, right? Because all of a sudden it's quiet. Then we can do even later, and you see what's happening now. We have a lot of unburned hydrocarbon, not so much NOx. We see that combustion is quite late, it's starting to get a little bit unstable. So all of this is measured data compiled into model. So this seems to be a little bit too late combustion phasing. So how about the boost pressure? How should I change boost pressure to make it earlier? Should I increase, decrease? Increase. So let's do that. Now I change the scale here. It's 300 bar. This virtual engine blows up at 280. So we shouldn't go above that, because then the program breaks. Okay, so it went earlier. So let's maybe reduce inlet temperature a little bit more. Later phasing. What's going to happen with compression ratio? If I now want to be a little bit earlier, should I increase or decrease compression ratio? Well, increase, of course. Because if you increase compression ratio, it means that pressure as well as temperature goes up. And that means earlier combustion phasing. If I want even earlier combustion phasing, I can do like this. Now the noise comes back. This is a really bad idea. How about this? This is how most people operate HCCI. Why? It's because we have quite a lot of safety margin. If combustion starts at 20 degrees before TDC, we have plenty of additional temperature to make sure it starts if something changes. But it's not a very good idea to do it. Efficiency is here not much, actually negative. So don't do that. Retard combustion phasing, and by that efficiency goes up. And eventually then it gets quiet. So that was compression ratio. How about speed? HCCI is a chemically driven process. It means that you heat up the charge. When the temperature is right, everything goes. Should there be any effect of engine speed? I take that as a yes. And what's going to happen if I increase engine speed? Well, it goes late. So, oops, now it seems like combustion is really late. Let's add some inlet temperature, like this. Oh, good. And then I could possibly go a little bit faster. Oops. Let's add a little bit more. Or maybe let's apply some boost. And then how about reducing compression a little bit? So what am I doing now? I'm trying to optimize the machine, and if you have nothing else to do, you play with this and look at the power here and try to maximize power. If you do a megawatt, you're good. Sometimes that works, and sometimes I just blow the engine. Oops, that's not very good. It's a large cycle-to-cycle variation because it's unstable. Some cycles it burns, sometimes not. So I saved it by adding a little bit more boost pressure, a little bit temperature. Right, we need to burn fuel to get more power. See, small steps. I think you're starting to get the idea how to do this. And it's not modeled, it's all measurement data. We measure the cycle-to-cycle variation from, well, as we do the measurements, and that's then part of the output of, what, should we call it a model? It's just a compilation of experimental data. Maybe that's a model as well, I'm not sure. So let's burn some more. And then I normally let students play with this program before going and run HCCI on a real machine. Why? It's because if you do a little bit like this, that's it. So, some HCCI results, and how many virtual engines do you blow up until you go and blow up real engines? Maybe a couple of hundred. How many real engines do you blow up before you get the PhD? Not a couple of hundred, maybe a few. So, when doing HCCI research, there are different ways to do it. You want to do thermodynamic engine studies, meaning you run a single-cylinder engine and you measure the efficiency, you measure the emissions, you're trying to understand why different variables affect the process. Then, once you find something really interesting, you go to the optical diagnostics. You try to measure what's happening in the cylinder and get additional knowledge from the optical diagnostics. That can also be used to verify and modify models. So some things you can measure, some things you cannot. And if you cannot measure it, let's model it. And hopefully you'll get more knowledge from that. The other branch here, engine control, that's multi-cylinder experiments. With the single-cylinder experiments like this, you could easily set conditions that would be totally unrealistic. And you can then easily get unrealistic results. Classical example, let's feed the engine with a 10 bar pressure in the inlet. Let's have no back pressure in the exhaust. Without burning any fuel, you get 10 bar work output. That's a really good efficiency. 10 bar output without burning fuel. But totally unrealistic, so stay away from that. You need to have complete engines with a complete gas exchange, and also you need to be able to operate in a transient mode. The HCCI operating range, if you do transient operation, is about twice as big as if you do steady-state operation. It's a huge difference. And the fifth one, fuel aspects. HCCI can run any fuel, but you need to know how the fuel is going to change the process, and vice versa, how the process is going to change the fuel behavior. So let's take a look at some results from all the 5 different areas. Let's start with the basic engine studies. Oops. What happened here? Interesting. So, there. This is the first HCCI paper from '97 from my research group in Lund. It was decided to go with HCCI because that seemed to be the combustion concept of the future at the time. And it is then a paper with isooctane, ethanol, and natural gas as those fuels being used. Why picking those? Well, as it happens, no one burned isooctane in HCCI before, so that's a world first. No one did ethanol, no one did natural gas, but why picking those anyway? Well, it's because there are simple fuels, or shall I say, well-specified fuels. So if we want to do modeling, we can actually do so. We can do chemical kinetic modeling with these fuels. If we would start with, let's say, gasoline, well, good luck, it's a couple of thousand components, and how would that affect things? Natural gas would have maybe 10, and the other two would be single components. So what we did, we took a truck engine, we modified the compression ratio to 21:1, and we then set 4 different inlet temperatures with a heater, and we then gradually added more and more fuel, from no fuel to more and more. So the highest lambda we measured was 9, so really high dilution, and then we're down to something like lambda 3. And we can see that with the highest inlet temperature, we can get the lowest load, meaning highest lambda. So pretty much no load at all in terms of IMAP here. As we then reduce inlet temperature, we see that the operating range is much more narrow. It's only here between 4 and 5 bar IMAP, and that means that the lean limit here is very much limited. Okay, so that's isooctane, and then we did the same with ethanol and natural gas, and we here stopped at 6.5 or so in lambda when it comes to the lean limit, 3.5 with natural gas. And we see that ethanol having a higher octane number, we did not do 40 degrees C in the inlet, there was no combustion. With natural gas, it needs to be the highest possible inlet temperature, otherwise nothing is happening. So, okay, good. Let's measure the efficiency. This is the gross indicated efficiency, and we see that it kind of hits 50%. So it's really high numbers without doing much. You just take an engine, you add some fuel, and that's it. You get above 50% gross indicated efficiency. Highest efficiency at the highest loads, because then the heat losses will be less dominant. This is the combustion efficiency, and there was this upper line here. That's the same engine operated stoichiometric with SI combustion. And we see that HCCI is not an efficient combustion concept, in a sense that converting the fuel to heat is not very efficient. The loss here from 100 down to like 90, that means 10% of the fuel is actually not burnt. And the conventional SI is twice as good in terms of losses due to combustion. So that's a little bit of a oops. So, efficiency with ethanol, kind of the same story, approaching and hitting slightly above 50% gross indicated. Here, though, we could get a little bit better control of combustion. So some operating points, we actually have a higher combustion efficiency than the conventional SI. So that's good. And same story with natural gas, kind of, but not very efficient combustion, but still a point above 50%. So high efficiency seems to be there, good. And then this is the way you should present NOx. Because what I'm showing here is NOx with HCCI in comparison to the conventional concept. And that's always how you should present results. Compare it to something familiar, and then it's much easier to understand the benefits. So this is SI, and we have something like 10 gram per kilowatt hour, so it's specific emissions. And HCCI is here some 3 orders of magnitude less. So that's isooctane, and this is ethanol and natural gas. And we see that with ethanol, it's even maybe a bigger difference, and not so much with natural gas. Natural gas is only like 1.5 or so order of magnitude difference. Why is that? Why do we generate NOx when burning natural gas? Well, it's the free temperatures of HCCI. You start with a certain temperature, you have a temperature increase due to combustion, and at higher loads here, It means that you're burning more fuel. You start at a high temperature, you burn a significant amount of fuel. It means that the peak temperature will be high enough to form NOx. So with natural gas, it's definitely possible to do high NOx HCCI. I'm pretty sure I have the world record in that one. I'm not sure it's very valuable though, but we've done, I think, 20, 30 gram of NOx per kilowatt hour. So it can be done, but of course there is no value in it. So unburned hydrocarbon and CO, you get about twice as much unburned hydrocarbon, and that's because of the low temperature and much harder to post-oxidize fuel hidden in crevices. I will show that in some detail. CO, well, we see that in some cases there is less CO. In some cases it's really bad, meaning not very good combustion at all. So same story pretty much with ethanol, and here we can see that the CO really creeps down, but we have a significant problem in unburned hydrocarbon. Yeah, same story with natural gas maybe. Okay, so this would be the first experiments we did, and we just set a certain inlet temperature. We had a compression ratio that kind of worked, and that means that the combustion phasing is totally random. So this model I showed you was done way later, where we actually did different combustion phasings and so on. Here it was only way early combustion, and that shouldn't be done. This is conventional SI, the dotted lines. The natural gas, actually a little bit better phasing, simply because the fuel wants higher temperature, and with the same temperature operated, then it gets kind of correct phasing, by accident pretty much. Okay, so fixed inlet temperature, not controlled combustion phasing, do not do that, and yeah, 2 lead mixtures as well. So that was the first experience with HCCI, but it also gives you kind of a framework. Unburned hydrocarbon CO would be high, NOx would be low, and efficiency would be high if you do it right, otherwise it's going to be a disaster. You've seen the free temperatures of HCCI before? Yes? Good. And that is still something that needs to be achieved. Meaning that if we sweep the inlet temperature, combustion phasing will change quite a lot. So this is a response from 150 down to 120 degrees in the inlet. It happens to be isooctane and with a 17:1 compression ratio. So what this is telling us is that if we want a slow burn combustion, it should be a late burn. It also tells us that even if temperature starts to drop here at TDC, because as we compress, temperature goes up, as we expand, temperature goes down. But even so, there is something cooking here early in the process. So even this very, very late combustion phasing, you release a little bit of heat before TDC, enough to get it cooking, and eventually it kicks in. But the later you go, the more unstable it is. You saw that in the model. You get a lot of cycle-to-cycle fluctuations because it's enough with maybe 1 degree C in the inlet changing to have a really dramatic change in combustion phasing. So going early is safe, easy, but not as good. The better control, the later you can go. Yeah, so combustion stability goes bad as you burn late. NOx drops as you go late, and unburned hydrocarbon and CO goes up. That's kind of what I already shown, maybe. So what's the optimum combustion phasing? That's actually not a fixed number. It's a function of load. If we operate really low load, like down here, yeah, by the way, these 3 here, blue, black, and Magneta, would be HCCI, and we see that at low load, it's much better to burn early. So this is when 50% of the heat is released. So burn early at low load, burn later at high load, and the regression line is pretty much 1-to-1. So burn roughly at TDC at low load, and then as you go to 6 bar load, then also have combustion phasing at 6 bar. Yeah, so this is a rich limit due to NOx. This is with natural gas, and you can see we're above 20 gram per kilowatt hour of NOx, and that's not very good. That happens to be a low compression ratio, and a low compression ratio means a higher inlet temperature, and that means this combination gives you much more NOx than the opposite, having a high compression ratio and low inlet temperature. So, yeah, and then we have the pressure oscillations. If you go rich, it burns really fast, and you get this knocking sound, as you heard from the yellow simulation. And that's a big annoyance. It's more annoyance than actually a disaster. It's very hard to break a HCCI machine just due to pressure oscillations. I never actually managed to do it. And believe me, I tried. So this is the optimum phasing. There is a limit in peak pressure that is more and more severe the higher the load. You have the combustion stability limit, you have the NOx limit, and eventually you hit the actual limit, meaning that it defines how high of a load you can go with HCCI. Yeah, okay, let's skip that. Fuel effects. I showed this already. This happens to be single-stage fuels, meaning that they just start to burn, and you're done. Other fuels are having a little bit more of a complex process. They start to burn, and then they kind of slow down again, regretting the starting. And then after a while, yeah, okay, let's do it anyway. So, so you have a start of pre-reactions. You release some heat, and then eventually it kicks in the main heat release. So it's a two-stage combustion process, and it's mainly larger molecules like N-octane or above that would experience these two-stage processes. Some isooctane only would show it, but normally not so much. So what's this? This is a mixture of isooctane and N-octane. So this is N-octane only, this is isooctane only, and we see that we get more or less of these pre-reactions. It's only the 100% octane that would not have any. We also see that the ignition temperature is pressure sensitive, meaning that higher pressure means we need less temperature to get going. Okay, these were obtained in this Volvo TD100 machine. You will see a lot of results from this machine today, and it's very flexible in a sense that there are only two valves, one inlet, one exhaust, and separate cylinder heads, and we got a lot of those cylinder heads, so we can play around with them. One of those ideas I got once was to do variable compression ratio, so VCR. So I told the technician, I want to do VCR, and he said, what? And I said, I want it done within the month, and he said, yes, and he actually did it. So what you see here is a cylinder head with an additional hole with a liner. This here is an additional piston that will be put in this liner, and it will be connected to a hydraulic system in the back end, so we can then move the piston up and down while operating the engine. Is this a really good VCR system? The range is, it depends on actually the volume you have when the piston is in the lower position. We selected that to be 10-to-1, and no, actually not. That was the minimum. It was actually, I think, 20-to-1, and then we could increase it, the upper piston position, so we were down to 10-to-1 compression ratio. The problem is if you go too extreme and have all the volume in this additional cylinder, it's becoming a little bit too much of Amir Farouk's experiments, a shock tube. So we should stay away from that. So it's too much of a long resonance pipe if we put all the volume in there. So it's actually the worst possible VCR system you can find, and the reason being that the piston rings here would have no lubrication. Well, of course, we filled the entire cylinder with grease, putting the piston in the lower position and then gradually increase it. That works, but when you're trying to move it in again, the piston rings slides on metal and not lube oil. And that means you do that a couple of times and then the piston rings are just seizing. So the average lifetime was like 2 days in the lab, and then we had to replace the piston rings and the liner, but that's okay in the lab. So don't do this at home, is kind of the message. But if you do it, you would get a result like this. So this is showing what compression ratio, inlet air temperature, and octane number combination would give us combustion phasing at TDC. So if you imagine this yellow background type of simulation, if there will be an additional slider saying octane number, that would be this axis here. And yeah, I do actually have a version of that program as well, but it's not for public release, so I can't show it. So it's telling us that if we're going to operate with a 100 octane number, meaning isoctane only, this line here is where we can choose compression ratio and inlet temperature. And that gives us pretty much the same temperature of the compression and hence the same combustion phasing. So that's good. And the line here is the same thing, but with N-octane only. By definition, 0 octane number. And it means that we need much less compression ratio with N-octane than we do with isoctane. How about this corner here? Well, we can't go below 10:1. And that means that the matrix is truncated here with 10:1 compression ratio. What is this telling us? It's telling us that doing HCCI type of work with a diesel fuel is an utterly stupid idea. Don't do it. If you do that, you need 10:1 compression ratio, and it will not give you any kind of an efficiency. If you do gasoline or high octane number fuels, well, then you're at 20:1, meaning high efficiency. Even so, there will be hundreds, thousands of papers trying to do HCCI with diesel fuels and failing. I will show a few of those. So this is isoctane and N-octane, the octane scale. This is gasoline and diesel. So not much changed, but it's another part of the matrix lacking. On the axis, this is diesel fuel only. This is gasoline fuel only, and then any mixture in between. So why is this corner here lacking? Well, it's because we operated the engine with port fuel injection and not direct fuel injection in the cylinder. And if you add diesel fuel in the inlet, it's not going to vaporize. It's a high boiling point fuel, and well, it's just going to pour into the cylinder, and there will be a pool fire on the piston. The H, like homogeneous charge, is not going to be there. So it's not HCCI combustion anymore. We could note, however, that if we crank up inlet temperature to 120 degrees, it's actually possible to do port fuel injection of diesel fuel with the low compression ratio and the low engine efficiency as a result. The title of the slide says multi-fuel capability is because if you adjust inlet temperature and or compression ratio, you can run any fuel, right? Doesn't really matter if it's gasoline or diesel, you can burn any fuel. Okay, any liquid or gaseous fuel, we didn't do any solids, I think, but yeah. Hydrogen, at this time, it's 2004, there was a lot of talk about fuel cells. I'm not sure, maybe they're coming back, maybe not. It's batteries and fuel cells, batteries, and well. Anyway, so we decided to run HCCI with hydrogen. Is that a good idea? Well, the answer is, again, no. Hydrogen chemistry is very, very simple. So once the conditions are right, boom, and it's done. So it's almost impossible to do late enough combustion phasing with hydrogen. It's very hard to get high efficiency because you're burning too early, and it's hard to actually get complete combustion burning all the hydrogen with HCCI. But still, we did it, world first, but stay away. Okay, back to real fuels, gasoline and diesel. NOx level from 0 to 0.05 gram per kilowatt hour. So all will be below this level I showed previously, this 0.05. And I guess we could go one number even less if so needed. Okay, basic engine studies. How about pressure oscillations? We did notice that the pressure trace get this ripple as we go rich. The question is why? We see the same ripple as we do SI engine knock. At SI engine knock, we know that we have a knock spot, and from this knock site, we get a pressure wave out through the combustion chamber. And this pressure wave then bounces back and forth, and of course that would generate the pressure oscillations. HCCI is supposed to be homogeneous combustion, right? No. Actually, all students saying so in an exam I'm giving would have total failure. So it's not a homogeneous combustion, but it's a distributed reaction. Would it be so that you actually have knock sites? Would you have a pressure wave building up, or would the entire thing just go pretty much simultaneously, like a big boom? If so, the pressure would be the same in the entire cylinder, but it would just fluctuate in time. Could it be that the connecting rod is just oscillating like a violin string? Who knows? So let's try, and we had a surplus of pressure sensors at the time, waiting for a multi-cylinder engine to be installed. So we had 8 pressure sensors, so let's fit them in one cylinder and hope that not all of them blows up at the same time. That would be way too expensive. So this is the pressure oscillation I just shown you. This is the TD100 I just showed you. And these will be the pressure traces, color-coded. You can see the color coding to the right. And you can see that, well, first of all, it's not the same, is it? The pressure in different locations will be totally different. So that's conclusion. Well, the title say hard to understand. I possibly would agree. But if you look at the few at a time, like these 3 here, we see that they kind of go in phase. That indicates that there is a wave coming from the upper left to the lower right at pretty much the same time. And if we look at the other ones up there, they also go in phase. Again, an indication that the pressure wave goes really upper left, lower right, and back and forth in that direction. It's kind of interesting. This is one cycle, and that's a master thesis generating one cycle of pressure trace. Of course, they did collect a few more, and if you look from cycle to cycle, you see that this is not at all the same process for the next cycle. Next cycle, it can easily be between channel 3 and 6, or it can be channel 2 and 5, or any other direction. totally random. But if we look at channel 4, 1, and 8, we see that it's really going in a very nice 180-degree phase. One goes high, the other one goes low. And we also see that in the middle, we measure a much lower amplitude, and we also measure pretty much twice the frequency. By the way, this is really good to know if you want to get really high load from HCCI without too much pressure oscillations. What you do then is to make sure that you fit the pressure sensor in the center and you see nothing. We tried that and got really high load in a Scania truck size machine, just replacing the fuel injector in the center with a pressure sensor. And that's the least sensitive position in the cylinder to put the sensor, and that also means for a certain maximum pressure rise rate, pressure oscillation, you can operate much harder. The only problem is that once we measured the length of the connecting rods, they were slightly shorter after the experiment. So we actually deformed the connecting rods. And the crank, and the block, yeah. Anyway, so this is the knock theory from 1938 from Draper, and there is different oscillation frequencies. You need to know the bore, local speed of sound, and I guess pi, and as well as this mode factor. And depending on how the pressure waves go back and forth, you would then get the different frequencies. And the lowest frequency here is this mode 1.0, just going back and forth like this, pretty much the mode I showed you, and is 1.8 here. And then you would see different modes depending on the complexity of the system. So we tried that with different bowl shapes. The pancake, then the diameter is really well defined. If we fit a bowl in piston like this, we have either this inner diameter or the outer diameter that could set up a frequency. And then we thought, how about doing something different, like putting a top here? That would cancel the mode, we thought, but actually it didn't. And yeah, there's a good agreement with theory. So the frequencies we detect is pretty much the ones expected from the 1938 theory. So that's good. There is also quite a big difference if you look at the frequency spectra of HCCI versus NOC. NOC is much wider spectra, seems to have more different waves in the process. HCCI is very much only one frequency, the base frequency, and the higher ones are very, very low in amplitude. This is the ringing index by James Eng. It's normally used to put a limit for any noise, and it's the pressure rise rate normalized by peak pressure, pretty much, and then you have some temperature coefficients, saying that the pressure rise rate is more severe if the pressure level as such would be lower. Okay, yeah, right. We had this machine, and we had 8 spark plugs as well. So how about throwing out all the pressure sensors and install 7 ion current measurement points and 1 pressure sensor. So ion current was that. It's just to apply a voltage over the spark plug, and then you measure the current flowing as you change the capacitance of the charge. And yeah, if you do that, you get something like this. You get 7 answers to 1 question, and the nasty thing is that those 7 questions change every time. So these 7 channels look like this. One cycle, the next cycle is a totally different story. There is a difference in phase, amplitude, rise rate, all of them from cycle to cycle. So it's very hard to use ion current for HCCI control, but I will show how to use it anyway. Okay, basic studies, unburned hydrocarbon. Let's do that also before the break. Recognize the engine. And the question was, Why so much unbound hydrocarbon, as we saw from the first paper, like twice as much from conventional SI? Is it only Crevice volumes? Is it bulk quenching, wall quenching? What's happening here? So we took the old engine. It's actually quite good to have an old engine, because that means you have a lot of different generations of hardware, and especially in this case, generations of pistons with different locations of the piston rings. So the location of the piston ring here, the ring pack, in comparison to the connecting rod bolt, would have 3 different levels. And that means, if you see here, it's quite a large distance from the upper piston ring to the upper part of the piston. So we could just add a spacer, bolt the spacer in place, and we can then change the width and height of the crevice. Doing a lot of those spacers, we also adjusted the height to maintain compression ratio the same. So 3 different pistons and different width, height, volumes of crevices, and we could then see, is it actually the crevice volume, is it the crevice width, or what is actually giving us the unburned hydrocarbons. So I'm not going to show all the results, then I will do nothing else today, but this is unburned hydrocarbon as a function of lambda with the narrow gap, and this is done as we widen the gap, and we see we get more unburned hydrocarbon with a wider gap until we go rich enough, and then we see that unburned hydrocarbon actually drops. That's when we start to get combustion into the crevice. So this is 1.3, 1.6. We get the combustion into the crevice a little bit earlier, meaning with a leaner mixture. So this is 2.1 and this is 2.8. And we see that the wider the gap, the leaner the mixture, we can operate and still get combustion into the crevice. This is, of course, a very suitable thing to model. And here is a multi-zone engine simulation is done at the Lawrence Livermore National Lab. It's actually a 2-step process. You first do CFD, and when combustion starts, you move that to a multi-zone chemical kinetic model. So we see this is with the narrow gap 0.26, and we have pretty much complete combustion in the bulk, but not much happening here in the crevices at all, and no combustion, pretty much. And as we widen the gap, we see that combustion goes into the crevice as we go fairly rich, lambda 2.5, and as we go lean, there is only partial oxidation here in the crevice. Yeah. So how about wall quenching? How can we measure wall quenching? Well, let's take some direct imaging. And what we see here is pictures from the side, as in the previous image, and as a function of crank angle. So this here is the pre-reactions. The scale is a bit strange, because yellow means maximum intensity, and then here is the dark black. It means that we have a lot of dynamic range, so a lot of signal to noise. So here we have a lot of combustion signal, here not so much, because the background is about the same color as the signal. But anyway, this tells us that combustion pretty much starts in the center, and there is not as much happening near the wall. And then eventually it changes, so combustion is completed in the bulk, and more action really close to the wall. So it seems to be a delayed reaction close to the wall, but maybe it's complete eventually anyway. So that's chemiluminescence. You only see that much with the camera. Let's do laser-induced fluorescence instead. And what we're now doing is to measure the fuel concentration with laser technique. And here's the fuel signal proportional to fuel amount. This axis here is distance to the wall. And we see that early on, meaning well before TDC, the fuel is pretty much homogeneous and not much happening. Here, far, far away from the wall, meaning 2 millimeters, it's dropping here just before TDC, and at TDC, fuel is gone. Would it mean that combustion is complete, but fuel is oxidized? So far away, things happen close to TDC, near the wall, and the wall here is actually the piston. And the stars indicates that the piston actually moves as a function of crank angle a little bit. And we see that there's definitely a delayed reaction next to the piston, but eventually most of the fuel, if not all the fuel, would be gone. So there seemed not to be much of a residual fuel, at least, near the wall. So maybe wall quenching is not the major factor. Crevices would definitely dominate. Yeah, so this is the same thing, but here 0 is the piston location, and here you have the fuel signal and the gradual drop in fuel signal, not so much near the wall in the beginning, but eventually it's gone. But the 3D looks much nicer, of course. And yeah, we did a wall boundary layer with velocity measurements as well, comparing this thickness of the near wall zone in velocity terms instead of fuel concentration terms. And they're kind of agreed. Okay, basic engine tests. The effect of turbulence on HCCI combustion. This started, yeah, you can see the paper is from 2002, and I got this, the student the assignment. Let's just verify that turbulence plays no role with HCCI. HCCI is a chemically driven process, right? So it's all about chemistry. So why would turbulence matter? It shouldn't, right? So let's just verify that nothing happens, and let's write a paper on that, and we're done with it. And so we did. The idea is to take 2 different setups in terms of fluid flow, one with a bowl, square bowling piston that we know is really fast burning in terms of HCCI combustion, really high turbulence. And then we take a disc. So what you see here is the upper part of the piston. And then we found 2 different cylinder heads to the old TD100, high and low swirl. And we then used 2 different cylinder heads, 2 different pistons, and that means we have 4 different combinations. And of course, we don't trust simulations, right? So we did the measurements in terms of the turbulence level. We did actually some simulations as well. But these will be the measurements. And it's the turbulence measured in the central point, as shown, the red dot. And we get this pecking order. The red, that's disk, low swirling head, less turbulence. We add some swirl, we get more turbulence. We get the bowl, and we get even more turbulence. And the highest one is with high swirl and the turbulent combustion chamber. So a nice 1, 2, 3, 4 in order. So this is the central point, and this is the corner point where we have the flow going into the bowl, and that's a high shear flow region with very much more turbulence with the bowl in piston shape. So it's still the same order, but a drastically increase in turbulence with the bowl. So all good. 4 different levels of turbulence, and then we measured heat release. And first of all, it actually responded. So that's the first observation, that turbulence actually matter. We get a difference as we change turbulence. But then if we look at the order here, so disk low swirling head, that's the lowest turbulence, and that's the fastest burn. And then this is the second fastest burn, more turbulence, more turbulence, more turbulence. So the same pecking order. The only problem is that the more turbulence you have, the slower the combustion. That's not exactly what's expected. In an SI combustion engine, higher turbulence really gives a faster burn. Here is the opposite. So what did I tell my student when he showed this data? Do it again. Yeah, that's exactly it. If you see something totally unexpected, you always blame the student, right? So he did. He first did, so this is with a start of combustion at 2 degrees before, and then we did at 3 degrees after. We get the same response. Once I told him to do it again and do not mess up the data files, he did it a few more times, and it was all consistent. We also changed turbulence in other ways. I think it was 17 different combinations, and they all aligned perfectly well along the line. The more turbulence, the slower the combustion. Okay, so I can't blame the student. Then what? Time to think. It kind of hurts, but you have to do it, right? What can turbulence combustion chamber do and change HCCI combustion? Could it be through heat losses? Could it be that we build up a different temperature field with the different heat losses? If heat losses increase, it means that the thermal efficiency should drop, right? So let's check that. And oops. The square higher turbulent combustion chamber would have a higher efficiency with the same combustion phasing. Nope. So that wasn't really the case. Okay, then what? What could it be? Could it be charge homogeneity? Turbulence is mixing, right? It's a good mixer. Could it be that higher the turbulence, the more homogeneous the charge? Well, this is a little bit of cheating, showing some of the high-speed diagnostics, but if we say that we have these kernels here starting, here we have a higher temperature in the kernel than we have outside. If we have much turbulence, it means that we take away heat from the high temperature kernel and we feed it to the colder surroundings. And the more turbulence, the more of this mechanism. So it means that take away heat from high temperature, add temperature to low temperature. Overall, that would reduce the temperature level, and then reaction rate would drop. Would that be a suitable explanation? Maybe. Why? How? What's happening? Let's do laser diagnostics. And I think this is possibly a really good time for a break. How long of a break should I take? 10. Okay, so back in 10. So before the break, I said strange things happens in HCCI. Turbulence gives us a slower combustion, and that's not expected. If anything, it will be nothing happening, or possibly a faster burn as in a SI, but not the case. So let's figure out why that is, and there were some thoughts. Most of them actually turned out to be wrong, but that's something that can be investigated once we can look into the actual combustion process. And that cannot be done with just chemiluminescence because we can't look into the combustion process as such. We can just look at the surface. So what do you need to do laser diagnostics? Well, you need a laser, you need a camera, and you need an optical engine. In this case, it's a YAG laser with a dye and just a camera set up for capturing a vertical laser sheet going through the optical engine. So that's the minimum requirement, those 3 components. And what we did, we started with measuring the fuel distribution, and just before combustion, because how does it look like really? So we had two different setups. We had fuel injection just next to the cylinder head. So there's a lower location here. That's called port fuel injection. What's shown here is 4 individual cycles. And it's a vertical laser sheet, something like 10 millimeters high and 40 millimeters wide. And the color is indicating fuel concentration. So black, less fuel, and the white, a lot of fuel. And it's clearly visible that the charge is not homogeneous that much. And we also see to the right part with the mixing tank, then it is actually homogeneous. You can see some, shall I say, random noise here. And this random noise is pretty much residuals from the measurement technique as such. Not really any significant fluctuation in actual concentration. So these will be captured just before combustion kicks in, and then how about as we start combustion? So these are the slides, or the pictures, which motivates me for flunking all students saying this is a homogeneous combustion. It's not. Color scale here, red is a lot of fuel left, and dark blue, not so much. And we see the 4 individual cycles again, and we see very steep gradients from zones containing a lot of fuel and zones containing pretty much no fuel at all. So it seems to be a very structured image. Combustion pretty much ongoing at least, meaning fuel is gone in some locations and not at all in other locations. We see that it's kind of the same story with the mixing tank. If anything, there are steeper gradients between burnt and unburnt zones with the mixing tank. Why showing both? Well, obviously we started with the port fuel injection and this picture. We said, oops, this is not really homogeneous, is it? And then we measured before combustion and said, oh, it's not really a perfect charge. And then we did the mixing tank and got the same results anyway. So this is fuel tracer, LIF, and this is OH, LIF, probing hot regions in the combustion chamber. And same story pretty much, that there will be really high temperature zones, very steep gradients to zones with pretty much no reaction. Why is this? What's happening here? And why does it look so totally random from cycle to cycle? How do we actually investigate the process? This kernel here, is this expanding? Is there like a flame propagating? So is HCCI actually flame propagation? If so, why is turbulence reducing combustion rate? The problem here is that you can't really follow the average process. In a spark ignition, you know that combustion is going to start at the spark plug and it's going to grow. So you can do a sample average type of statistical analysis. If you would take the average of all 4 here, it will be just a homogeneous signal. If you take the average of a couple of hundred, 1,000, it's very much a smooth surface. So on average, it's really distributed, but a single cycle is not. And we can't really follow the local individual process without having a cycle resolved measurement. So what we need is then, well, a system that was built at Combustion Physics group in Lund. So to summarize, very simple, you take 8 lasers and put in a box, and then you take 8 cameras and put in another box, and that means you get 8 pictures. Do not use 8 optical engines though. And make sure that the 8 laser sheets actually would be at the same place. That takes half a year roughly of alignment, and then you need to align the cameras as well. And that's not trivial. But once everything works, you get a movie like this. And that is not really starting, but anyway, it doesn't really matter. You see the 8 pictures anyway. So it's not really a full-length feature. It's only 8 pictures. But 8 pictures in the same cycle means that we can follow the process and we can see what's actually happening. And what we saw was kind of a large change of behavior from the beginning of the combustion process to the middle and the end. In the beginning of the combustion process, it is very much a homogeneous reduction of signal intensity. So a homogeneous breakdown of fuel, if you like. But if we look from one picture to the next, it really amplifies the small structures you see. It is maybe most visible here between 3.5 and 4 degrees, maybe from 4.5, that you have a transition from pretty much a homogeneous reduction of signal intensity to a very structured image. And actually the maximum signal intensity here at 5 is higher than you would have here at 2. So we have actually a gradual compression of unreacted regions in this HCCI process. So you go from a very homogeneous to a very structured image, and that was the first time that was shown here at 2002 or so. So back to this pancake versus bowl combustion chambers, and why is it that the bowl is so much slower, even though it has much higher turbulence? So this is the quartz piston crown with the bowl geometry, and this one is then fitted within an optical liner, so we can have full access into the bowl. The lifetime of this particular device was 2 seconds, and the second one of the same shape worked for 2 months. That was exactly the lifetime of the measurement campaign as such. And it was actually planned that way, strangely enough. Anyway, so this is the pancake geometry, and the high-speed video is the same as I showed in the introduction. It starts in the lower left corner, roughly, and then it progresses, and here you can see it, and then more signal will be in the center when before completion. So these will be the snapshots, and we can then see this start here in many different locations. This is one single cycle. The next cycle will look different. You can see pretty much the hole in the center, and then more of the signal in the center. And then it's kind of done. And the combustion process is in the range of maybe 10 degrees crank angle or so. This is with the bowl, and here something else is happening. It actually starts in the corner here, and then it's progressing pretty much doing one revolution in the bowl. And it pretty much starts in a spot and doing a movement of the reaction zone, and it's only very late in the cycle you see something in terms of combustion outside the bowl. So if we again look at the snapshots, in the upper right corner, so 19 out of 20 cycles is starting in that corner, and the 20th one, it was in a different corner. But pretty much always in the same corner, and doing one loop here, and we see that it starts at -12 and is down by plus 14 or so. Very much longer combustion duration, because it's not happening in many places, only a few places at the same time. So that was high-speed video. We did the same with the laser diagnostics, kind of giving the same signal. But did I explain? Not really, did I? So it's kind of annoying that we couldn't really explain it with laser diagnostics. We have to move into modeling. So you can actually use modeling for something. Right, Hong? Good. So this is a cycle-to-cycle variation, still experimental data. This is formaldehyde, and this is OH. Just showing that in a dozen or so different cycles, it looks very much different. Why I'm showing this is because it's justifying not using RANS type of models. And that's why I'm also using a black background for this one. The student thought it was a good idea to use a blue color scale, which is not. But the lower line here is the average over many cycles of the combustion process, and the upper one is individual cycles. And hopefully you can see that there is a lot more structures here with single cycles than if you take the average over many cycles. RANS modeling, as I understand it, is really the average over many cycles. So that's why LES is a very much better tool for HCCI. Combustion is not homogeneous. So again, this is experimental data, formaldehyde, OH, and this is the formaldehyde in the LES simulation and the OH, and also the temperature field, showing that it's not at all a homogeneous temperature field with HCCI. Okay, all good. This is just to show that, yeah, you see these structures also visible in the experimental measurements. So what's this? This is a progress variable of some sort, showing that here, the red, there is a lot more reactions ongoing or actually completed. And if we put the tracker, like the plus and the ring here, down there and there, we can then calculate what will be the virtual speed of those reactions moving. So if we move around here a few steps, we see that the reactions are moving, and we can calculate, this is, well, 40 to 10 meters per second, depending on if you do absolute or Lagrangian scale, or the flame propagation is in the range of like a little bit less than 10 meters per second. So velocities seems to be kind of where you expect a turbulent flame speed to be. Anyway, so this is the explanation. Why is higher turbulence giving us a lower burn rate? Careful. So what we see here is an inlet stroke with the bowl combustion chamber. The color scale is temperature, and we see that there is significant heating of the charge from the hot walls during the inlet and early compression stroke. And this generates quite a stratified temperature charge, meaning that in some parts of the combustion chamber, temperature is high, meaning reaction starts. And where would the temperature be the highest? That's where we have the most wall per volume. And where's that? That's in the corner of the bowl. You can see here, if you follow the temperature here in the bowl, that's significantly higher than the average in the cylinder. During the inlet stroke, during the compression stroke, and also it's going to go here in that corner, and then progress through the bowl. So actually, turbulence gives you more temperature stratification, giving you a slower burn, because you start burning the high temperature zones and then you burn the low temperature zones. So you extend the burn process and longer burn duration. So that was the final conclusion, why this strange combustion chamber is actually giving you a slower burn, behaving pretty much like ASI. So this is the LES simulation of the same as the high-speed video. And we see it starts in a corner. For some reason, it starts in the lower right instead of the upper right corner. We spent quite some time trying to figure out why the CFD predicted the wrong corner. Turned out to be kind of a easy way to explain it. This is looking at the combustion chamber from above, and the measurements were done from below. So it's actually the same corner, but different view. Okay, enough of that. Let's do some closed-loop combustion control. I said without it, the engine explodes in a few seconds. Why do we want to do closed loop control? We want to burn as much fuel as possible to get a higher load of HCCI. So this is kind of the limit, and this is something I showed previously. If we burn late, the burn rate is less, and that means we can go up in load. So let's phase combustion late. But that also makes the entire system very nervous. So we need to measure what's happening, and we need to adjust something to the next cycle so we stabilize. So if combustion is a little bit too late, let's add some more temperature to the next cycle, and vice versa. So this is the first closed-loop combustion control, and we selected fuel as the control variable. So instead of changing temperature, changing compression ratio or something, we changed the fuel octane number. And we do that by simply blending isooctane and octane with 2 port fuel injection systems. So we can inject either isooctane or N-octane or any mixture in between, and we can decide that on a cycle-to-cycle basis. So all this here is just to measure the in-cylinder pressure trace, calculate what's happening, set up some control parameters, and then decide how to inject. So this is the quick version of how to do a heat release analysis based on in-cylinder pressure. So we measure the pressure trace, you compress, you burn, you expand. You take this heat release equation saying that if we know the pressure and its derivative, the volume and its derivative, we get how much heat is released per time step. If we integrate that, we get this rate of heat released type of curve. We detect where is 50% of the heat released, and this crank angle is called CA50. The crank angle position where 50% of the fuel is burned. And that would then be our control variable. This one should be at a certain crank angle position. And yeah, well, you can do ion current instead of pressure sensor. Toll is not really very good, but it could give you some indication of what's happening. On the y-axis is the ion current, and on the x-axis is the real thing, meaning CA50. And yeah, there's some correlation. The plus and the x would be 2 different operating conditions. So, how can you control the HCCI? Well, you can do this dual fuel, meaning blending isooctane and octane. So this is done here in a Scania multi-cylinder truck engine. You can do variable valve timing, meaning that you can change when you close the inlet valve, and by that you effectively change the compression ratio, the effective compression ratio. You can also change how much you trap residuals with the valve timing. I will show that a little bit more in detail eventually. That's done here in a Volvo car in line 6. The previous one was a Volvo truck. And this is with the variable compression ratio and inlet temperature control. So we done all that, and it kind of worked, most of it. This is the tilting engine with adjusting the compression ratio by pulling this lever, actually with a hydraulic system. And the basic idea is then to use this variable here, compression ratio. And doing so, you can run any fuel and pretty much any inlet temperature. So that's good. This is the dual fuel, and we did operate up to 280 kilowatts. That's roughly 90% of the diesel engine peak power. And without closed loop control, the maximum load will be around there, roughly. So you do not try to go high load without closed loop control. You're simply not fast enough to control it yourself. And if it's a 6-cylinder engine, you need 7 students to control it. So 1 per cylinder, and the 7th one to control inlet temperature. And I don't see that happening easily. So this is a typical cycle with this closed loop control, 20.4 bar IMAP and 17 bar with the net. with gas exchange. And we're hitting 200 bar peak pressure because the engine supplier, Scania, told us to not go above 200. So of course we didn't too much. This is of course the published data. There were some excursions to 250, 300, and yeah. Okay, in order to do this closed loop control, you need to adapt to the operating point. You need gain scheduling, meaning that the engine is not behaving the same running idle as running really nervous high load operating points. So you need something called a sensitivity function. That's a function of speed, inlet temperature, fuel mass, octane number, and combustion phasing as such. So this one here has a function of octane number. It's shown here. As you can see, it's highly non-linear. And you need to have non-linear control to get this to work. The reason being, on the y-axis here is this combustion phasing you want to control. On the x-axis is the octane number. That's your control variable. The different lines here is showing different operating conditions. So here it's a low load idling point, and we see that the gain here is kind of low here. You need to change octane number like 10 units to get a few degrees change of CA50. And here it's a totally different story. You change octane number 1 unit and you get 10 degrees change of combustion phasing. So if you would use the controller gain of this point here, it will be totally unstable, and then you would malfunction in seconds. And vice versa, of course. Not good. With the control, you can actually stabilize unstable operating points. What I'm showing here is a step response in combustion phasing. This particular case, we are using natural gas and hydrogen as the two fuels. Hydrogen being used as ignition improver for natural gas. So more hydrogen means more reactive charge, meaning earlier combustion phasing. So here at this particular point, we say, let's go earlier combustion phasing. And we do that by simply adding more hydrogen. But then earlier combustion phasing means we need less ignition improver because we heat up the walls, and that gives us less need of this hydrogen. And we see that as a gradual decrease of the hydrogen after the step response. But this is a stable point, so no problem. This is an unstable point. And here we go from a late to an early with a step response. We see the small kick in hydrogen needed, but then we see a massive increase of wall temperature, reducing the need of hydrogen. So actually here we have less hydrogen with the earlier combustion phasing. And that's an unstable control. But if you have the correct control system, you can stabilize and operate anyway. So here at 0, we switch off the controls. In the red operating point, it's stable. So we repeat it 3-4 times, and nothing really happens. Boring. Here, we repeat the experiment 3 times. In 2 cases, combustion goes earlier, and eventually the engine will explode. In one of the cases, combustion goes later and later. Eventually, it will quench out completely. We're going to pump all the fuel to the exhaust, and the exhaust pipe is going to explode. So no good in any case, but we can operate a higher load with this stabilizing system in place. So, so far the HCCI results, we've done 90% of the maximum power, 20.4 bar IMAP, 17,000 RPM with a small 2-stroke. We did closed loop control and laser diagnostics to understand, possibly with the aid of CFD. About here, I always get the question, so when is HCCI going to make it into production? I said, yeah, well, you see the number 1890. That passed, right? So it means that it should be in production by now. Well, it was, but not anymore, or is it? So this is the Ackroyd hot bulb engine from 1890. So the picture is from the Science Museum in London before they converted the engine expo to the entrance of the IMAX theater. Anyway, here's the low pressure fuel pump. You pump fuel into the bulb. In the bulb, there is only residual gas from previous cycle. So fuel is not enough to burn. You need oxygen as well, right? Oxygen you get as the piston doing its compression stroke. You feed in air, so you have air, fuel, and some temperature, and boom, off it goes. So it's not really homogeneous, but there is no spark plug, there is no fuel injection at close to combustion event. So by that, let's call it HCCI. So these hot bulb engines were very popular in Scandinavia. Small shipping or fishing boats, agricultural devices, tractors. This is a drawing from the Smithsonian, and I'm pretty sure a Swede was there stealing the drawing, because most of the Swedish hot bulbs will be this design. So what you can see here is the bulb. Here is the fuel injection going to the lip, and then it bounces into here. This is the starting device. It's a blowtorch to heat up the bulb. That takes only like half an hour, so no panic. But it was very robust and worked very well. No spark plug that fouled, and could burn cheap fuel like kerosene or naphtha. And so this is the efficiency of different engines. The same student having nothing else to do, doing this simulation thing with a yellow background. He also compiled some data from Lund University Library. Lund University Library collects everything written in Sweden. Everything. Including also all the measurement data from tractors. He just asked for those data and compiled the results. So the rings here would be hot bulbs. The blue scatter would be different diesels, and the green would be different spark ignition, or equivalent hot bulb or hot tube. And yeah, this is pre-chamber, swirl chamber, and direct injection diesels. So we see that low load hot bulb is kind of the envelope. So the best machines would be hot bulbs. Some of the worst would also be hot bulbs down here. But it seems to be possible to go quite high in efficiency, even though the compression ratio was 2.5 or so. Yeah, we put one in the lab. This is the invisible engine. We took it from a museum. It's from 1932, and why does it be the invisible engine? It's because it was putting here on the sledge. It's an 8-liter engine operated at 300 RPM or so, with not much of a balancing system. So it was actually oscillating about this much. So when operating, it was kind of, can you see my hand? No? Kind of the same story with the hot bulb engine. It was moving so much, so it became invisible. It's also broke the dyno a few times, but it turned out to be pretty much HCCI-like emissions of NOx and reasonably good efficiency. So, but no one actually knew about the emission levels because they became obsolete before the invention of emissions, so to speak. So here's one of those two-cylinder hot bulb engines in a tractor. You can see the bulbs up here, here, and here. They are semi-cooled, meaning the lower part is cooled with water, but the upper part's not. Here you can see a student of mine heating up the bulbs from his father's tractor. That was before we went out plowing with this tractor. It was really fun. So I've been driving HCCI on a field. Cool. Why not a major success today? I would expect no one would really be interested in taking out the blowtorch and for starting, co-starting the engine and heating it up for half an hour. Not going to happen. Well, who did HCCI the first? Well, Otto, you know the guy with the four-stroke engine. He invented his four-stroke in 1876. In 1860, he kind of designed his engine number 0. Well, he did number 1 as well before the four-stroke became number 2. He had no clue about combustion, so he did no compression volume. That means infinity to 1 compression ratio. We know what's going to happen if you mix fuel and air and you compress it to high enough pressure, temperature. It's called HCCI, right? Boom. And he got so violent combustion, so he spent the rest of his career trying to avoid HCCI. He even did this optical engine with a special design, air cushion, burnt gas cushion, to avoid the very violent combustion, which of course he didn't know was HCCI, but it was. And 3 out of 4 claims in his four-stroke patent was to avoid this with a stratified charge, which of course didn't work, but that's another story. Diesel, the other guy, when he did his experiments, he concluded that combustion started when reaching 20 atmosphere pressure. That was a little bit of a surprise, since that was during the compression stroke, and he injected fuel at TDC. So combustion started before he injected fuel. Well, he tried a few times, and if you try and try and try, you add fuel, you add fuel, you add fuel, eventually you have enough to do HCCI. So diesel almost got killed by the HCCI engine, in a sense that he got so violent combustion, so the safety valve flew off and landed in the wall, half a meter away from diesel himself. If he would have been in that location, well, I guess HCCI would have killed diesel. Okay, enough of that. Let's look at some more practical, if so, paths. Very much happened in 1998. Honda released their commercial 2-stroke running HCCI. Nissan released the MK combustion concept. K stands for Kimura. I still don't remember the M, but still. Kimura himself was here a year ago giving a talk at KAUST. And Unibus was released by Toyota. Ford presented a concept with OKP, and well, the VCR thing with the Saab together with Lund was at the same time. So a lot of things happened, and first is the 2-stroke. And what you do with the 2-stroke is that you trap hot residuals. So you see this big valve here. That is adjusted up and down. So now it's in the lower position, meaning that you have a very long expansion stroke, and hence also compression stroke. And you trap a lot of residuals because you can't get the fresh air in and the exhaust out in a very good way. So with this yellow point, you can control the effective compression ratio as well as the amount of dilution, as well as the temperature. Because if you trap a lot of exhaust, temperature is high, right? So it's enough to close this point to get from conventional SI combustion to what they call AR, and then you open it again and you get the conventional SI. So this is a part load operating scheme, and you go conventional SI when you want maximum power, and here you want better efficiency, lower emissions, and then you convert to AR. So this is a scooter, very similar to the ones you find here at KAUST, the 125cc, but this is a Honda instead of a Suzuki. And here you can see unbound hydrocarbon drops a lot, if you remember from my initial slides, ambient hydrocarbon was like twice as much with HCCI. Here, it's less than half. I showed 2-3 orders of magnitude lower NOx, and now it's about the same. So when implementing HCCI in the two-stroke, you don't get the same results. There is no difference really in NOx level. Reduction of ambient hydrocarbon. Fuel economy, very much better. So efficiency is very much better. So do we trust the data from Honda? Of course not. So let's get one of those. Okay, so this is combustion stability. This is the standard SI combustion, and this is HCCI. And as you can see, it's very much more stable with HCCI. So we didn't trust Honda, so we took one of those, and this was a master project. So take the scooter, mount it in the test bench, add an emission analyzer, and then measure the CO, NOx, ambient hydrocarbon, and the fuel consumption. And yeah, we got kind of the same numbers as Honda. So seems to be about right. This is just a zoom in, and sure enough, the NOx level, there is no major difference if you do SI or HCCI. And fuel consumption is improved, but well, main conclusion, there is no NOx benefit doing two-stroke HCCI. Ambient hydrocarbon, 30% less, but still high, and much better combustion stability at low. And yeah, brake efficiency is improved, but it's still less than 20%, so who cares? It's not good. Then someone got the idea of, if we can do this in a two-stroke, how about doing it in a four-stroke? So how about converting a four-stroke engine to the same conditions as ARC? Let's keep the compression ratio about the same. Let's not heat the inlet air, but let's trap a lot of hot residuals by closing the exhaust valve early and opening the inlet valve late. It's called negative valve overlap, meaning no valve overlap. And doing so, we trap hot residuals, and we get the same in-cylinder conditions as the two-stroke. And the only thing we need to do is actually to change the valve timing. And then a conventional SI engine, all of a sudden, will be HCCI. Good. Changing valve timing, that's done with the active valve train, and that can be easily done from cycle to cycle. So this is a conventional valve lift exhaust inlet. This is then the short duration and closing early and then opening the inlet late. And that then enables the HCCI. You can also convert gasoline to diesel by injecting fuel in the wrong TDC, because if you close the exhaust valve, you get a recompression. That means in the wrong TDC, temperature, pressure is fairly high, not quite high for combustion, but high enough to get the fuel cooking a little bit. So if we inject the fuel here, we actually convert the low reactivity gasoline to high reactivity something else. Let's call it diesel-like. So it means that if we inject a certain amount of fuel here and the rest where we normally do, we can then balance and adjust the fuel quality by simply selecting when and how much we inject the fuel. And then we have another control variable. So that seems to be doable. And so we did that and tested it in this inline 6 and concluded that, yeah, it's kind of possible, but you either get 4-bar IMAP at 1,000 RPM or you get 1 bar at 4,000 RPM. So it's kind of the same power. Why is that? Well, it's because it's really one setting that gives you the right balance between dilution, meaning burnt gases, and temperature from the exhaust. And that's pretty much only one
power rating of the machine. So IMAP times speed gives you power. So the temperature of the residuals is not high enough to start auto-ignition as we go down. And as we go up, we're starting to get asthma, meaning hard to breathe. We can't really get the air in. GM, though, said that they're moving it close to market, but that was 2007. And I guess they're still moving it close to market, but not close enough. They did have demo vehicles out there showing that, yeah, it can be used. The problem is that the operating range is not sufficient, and the efficiency gain with controlled auto-ignition is not good enough to justify putting it in production. So if you compare it to the two-stroke, this lower triangle is about the same, but the limit here is a little bit different at first hand, but actually we see it's kind of a constant BMAP here in the two-stroke, but in relation to maximum BMAP you can achieve, it's actually about the same. So it's dropping here simply because a four-stroke would have more of a constant line here in peak torque. Okay, enough of that, and the VCR, much better solution. You can run any speed load point by adjusting, and you have then an independent control of temperature and dilution, and that gives you a much higher efficiency. Yeah, so this is the FTM. The idea is to take exhaust heat and you feed it to a heat exchanger, and then you heat the inlet air, and this would then go into the cylinder. You have a second path of air going into the cylinder as well, and you then select, should I take hot air, cold air, and depending on how much I choose from the two, you get then a really fast response inlet to temperature. It's kind of the same as taking a shower. When you take a shower, you conclude that, it's kind of a little bit hot. Do you go out and adjust the temperature of the boiler tank? Possibly not. What you do is that you blend with cold water. And this is the same principle. You have a hot and a cold source, and then you blend to get what you want. And that you do in 0.1 second roughly. And this one I just showed, I skipped that, and this is just to show the brake efficiency we got, 40 and a bit, and very low NOx and so on. Okay, the diesel concept, Nissan MK, they can do it at part load. And how do they do it? Well, first, well, it's been in production since '98. I think there are still versions out there. And the basic idea is to mix fast and slow down chemistry. And mixing fast, you do with a high swirl level. So they have up to 10 to 1 in swirl, really fast rotating flow in the cylinder, and that's much higher than the normal 3.5. 3.5 is actually fairly high as well. But the 3 steps Nissan is doing to get into the MK operating range. First, they reduce the amount of oxygen in the inlet, meaning using exhaust back into the inlet. So from 21 to 15% oxygen concentration, that's step 1. But doing so, you increase unbound hydrocarbon and you increase soot quite a lot, even though NOx drops a factor of 6 or so. Then they retard injection timing, and by that you increase unbound hydrocarbon even more, but you drop in soot. And then the final stage is to apply this high swirl combustion concept. And then finally unbound hydrocarbon drops and the soot goes down to very low numbers. So by doing all 3 steps, you can reduce unbound hydrocarbon, NOx, and soot, all 3 at the same time. But you need to do all 3 steps, otherwise it's not very good. So this works at fairly low load, because then you do not need to inject that much fuel, and the ignition delay is reasonably short. So they want to inject the fuel, so like here, and that should be done before combustion starts. At higher loads, you need to inject more fuel, takes more time, and the ignition delay actually shrinks down. So then there is no time to get all the fuel in before it starts to burn, and then you're not in the MK combustion mode anymore. Caterpillar did show that you can do this at higher loads by simply adding more media, and they compared the MK and the red one, first and second generation. Well, this is a target, and then their own data, and it's about 20 bar BMAP in what they called HCCI mode. This is the full load operating point, and it's fairly good numbers, 0.0 something in NOx, and low soot, and so on. All good. The Unibus, actually, I'm going to present that later. So what's RCCI? RCCI is a version of HCCI with an R in the beginning. This R stands for reactivity controlled, or possibly it's because the inventor is Rolf Reitz. So why is it not called RRCI? Well, you need to ask him. I did, he didn't really answer me. So the basic idea is to do HCCI with two different fuels, high octane number fuel in the inlet and high cetane or low octane fuel during the compression stroke. And by doing so, changing the ratio of high and low octane fuel is the same as I just showed in the controls chapter with, changing the octane number based on operating point. But doing direct injection of the high cetane fuel also means that you would have a stratification in octane number in the cylinder. So in some regions, it would start to react, and in other parts, it would not react as fast. So the normal set point is most of the fuel port fuel injected, or very, very early injection, and then two injection pulses, one at 60 and one at 30 degrees before TDC, with the diesel-like fuel. And so the first results will be from 2010, I guess, diesel, and they then used a Caterpillar single-cylinder engine equipped with variable valve timing to control, and they did operate with ethanol and diesel blend, or E85. So I guess it's ethanol, gasoline, diesel. And this operating point here generated a lot of buzz in the engine community because it's 59% indicated efficiency. And that's very high. And the reason being it can be so high is that it's a fully optimized heat release pattern, and it's a fully optimized, well, this is a zoom in, and it's a fully optimized thermodynamic cycle with a late inlet valve closing, and that would give you a bump in efficiency. So, well, I just did some ideal cycle calculations, and it turned out that it's very, very high, and it's very, very close to an ideal cycle, provided that you do not take the overexpansion into account. The overexpansion will give you higher efficiency. The basic idea is that you compress from, let's say, 1 to 2, you burn, you expand, and instead of releasing the gas here at 4 prime, you go to 4 or even to 5 star. And then you open the exhaust valve. So you would have a longer exhaust stroke or expansion stroke than you would have compression stroke. And that means this overexpansion will give you an efficiency. This is from the Haywood textbook showing how much improvement in efficiency would you get. And so this is 100% or 1. And we see that if we start with a low compression ratio, we get up to 40% improvement in efficiency with this ideal cycle. But the lower IMAP would also be a result. You will get less work output from the cycle. So that means the friction will be worse. Yeah, we did that, but I think actually I'm going to skip that. Oops. So spark-assisted compression ignition, what's that? Well, it's this. Or it's not. That's interesting. It's not really starting. Let's see if it actually kicks in once this is completed. Could be. Yep. So you have a flame to start with, kind of the same as a SI, but there will be an additional flame starting from elsewhere. This movie I sometimes use to explain how NOC works. So you have an additional point where combustion starts, and this is kind of the same, but it's not. What's the difference? The difference is that once you get this additional combustion, it's reasonably slow. And it's reasonably slow because it's really high dilution. And it's diluted, so the normal flame is slow, and the HCCI part is also slow. So kind of the same as NOC, but not quite. And it's controlled instead of extremely fast NOC process. Doesn't really work well, so let's go to PPC instead. The PPC, it's a one step back, but it's also boosting efficiency. With HCCI, maybe 47% indicated is where you're going to be with a realistic condition. With PPC, it's 57. So it's a significant step forward. So as big of a step from SI to HCCI would be HCCI to PPC. As I said, 57% efficiency, and that is with a suitable fuel. And the suitable fuel is a low octane number gasoline. So you should operate the diesel engine on gasoline to get the best possible efficiency and to maximize the benefit of this partially premixed combustion. If you wonder about the numbers here, that will be different fuels from Chevron. So this is a fuel number 47,333 since they started to blend fuels at Chevron. And that happens to be a low octane number gasoline. Okay, for the PPC part, this is the idea. First, HCCI and the fuel efficiency. I haven't really talked about efficiency much since I showed the results from the first paper. So let's do that first, and then what is actually PPC? Why is gasoline the best possible fuel for a diesel engine? I'm going to show 56% thermal efficiency in the car size engine, 57 in a truck, and then I'm going to explain why 55 is better than 57, and then how to reach full load with emission compliance without after-treatment. So let's start with HCCI and efficiencies, and possibly I should have started my talk with this, but I did not. So any engine efficiency would be divided in 4 parts. It's the combustion, thermodynamic, gas exchange, and mechanical efficiency. It doesn't really matter if this is 100%, if this one is 0. If any of these will be very low, the total efficiency will be very low. So it's all about optimizing, and it normally is that if this thermodynamic efficiency is really good, the mechanical efficiency is really bad, and vice versa. So the combustion efficiency, that's going from fuel to heat, and the efficiency is then combustion efficiency. Losses would be something that could have been burnt but was not in the exhaust. And then from heat to work on the piston, that's a thermodynamic efficiency. Going from compression expansion strokes to all four is the gas exchange. Pumping losses being the loss. And finally, going from all four strokes on the pressure on the piston to output power, then it's the mechanical efficiency and friction losses being what we are losing out. Here you have the Sankey diagram kind of showing the same thing. I try to use mean effective pressures for all the numbers. So that's energy normalized by displacement volume of the engine. So that's the equivalent of dimensionless numbers in the engine community, and use them. So I showed this before, just highlighting that HCCI could be good. Now we're ready to see what's on the y-axis. Is the thermodynamic efficiency, meaning it's from heat to work on the piston. And HCCI is really good, like hitting 50% or so, meaning that if combustion would be complete, if the gas exchange would be without losses and there would be no friction, the engine would have 50% brake efficiency. Well, that's not going to be the case. The question is, how much are we going to lose in each step? So we need to, yeah, by the way, this is the variable compression ratio Saab. This is inline 4. It's the world engine. We ran it in HCCI with 18:1 compression ratio. We run it in SI with the same compression ratio on 9.5 standard SI. And then is the truck size engine, Scania, also with 18:1 compression ratio. And the VCR engine, we ran up to 30:1 compression ratio. So, as I said, thermodynamic efficiency is 1 out of 4. And do not focus only on this one. Here we see that the HCCI is not very good in terms of combustion efficiency. Conventional SI is actually much better. Diesel would be here in 99.9 maybe. Very much better. Gas exchange, it is a significant advantage, not throttling the engine, so HCCI is better. This one here, the blue, not having a turbo, that's good at low load because the turbo is in the way, giving us a little bit of throttling losses. Mechanical efficiency, all good. If we increase peak pressure, we pay a little bit in friction. And how about this guy here? That's an engine designed to operate at really high loads, but is now operated at low. And that's a bad thing. Don't do that. So, the problem with HCCI is that it's burning too fast. So we see that it's in range of 5, maybe 10 degrees crank angle, burn duration, and that's too fast. That's giving us too much noise, too much heat transfer, and we really don't want to go that fast. We would like to go like this, but it's then extremely sensitive and it's very hard to control. So what we would like to do instead is partially premixed combustion. And with PPC, we can put the correct combustion phasing with the correct combustion duration, and we can design that by injecting the fuel at the right time and at the right rate. So we can actually engineer our heat release curve as we want it. So what is PPC? It's explained by this slide here. This is when we inject the fuel. So 180 degrees before top dead position, it means that, well, plenty of time for the fuel and air to mix before combustion starts. So that's HCCI. If we inject very late, it means there is no delay from fuel injection to combustion starts, and it means that it's pretty much conventional diesel combustion. There is a dramatic change in NOx here is like 1 ppm because it's fully homogeneous, no stoichiometric zones giving a lot of NOx. As we then retard, we go up to 1,000, so 3 orders of magnitude higher NOx level by injecting too late, moving to conventional diesel combustion. But we also see the blue line here. That's unbound hydrocarbon, or should I say combustion losses. So putting the fuel in the cylinder way early means that we put fuel in the crevices. Crevices is not a very good place to have fuel because that would give us poor combustion efficiency. As shown when I showed these many different piston crowns and modifying the Crevice volumes. So injecting the fuel very late means that unbound hydrocarbon drops a couple of orders of magnitude. So a factor of 100 or so, and that's really good. So we want to inject here for unbound hydrocarbon, and we want to inject like here for NOx. So the aim of the game is to open up this window here and make partially premixed combustion with very low NOx, very low unbound hydrocarbon at the same time. So how do we do this? How do we open up this window and widen it enough to make PPC viable? That's kind of the aim of the game. So yeah, there's a lot of different abbreviations and so on. HCCI was that. Well, that's normally with port fuel injection and high compression ratio. Controlled auto-ignition, that's normally with a low compression ratio, high residual gas content. PCCI is normally with a rather early direct injection, forming a rather homogeneous charge, whatever that is. PHCCI is kind of the same as PCCI, well, another inventor. Partially premixed combustion, PPC, a little bit less homogeneous. And if you can't make up your mind, call it low temperature combustion, and it's covering it all. I do have a more extensive list of different abbreviations. I think it's like 25 or so different, explaining the same thing. So why calling it PPC? Why changing this? Well, it's because before 2008, we published some papers we called Stratified Spark-Assisted HCCI. So wait a minute. So it's stratified homogeneous, and it's spark-ignited compression ignition. So PPC is more of a neutral, easier word, because it's partially premixed. So it's kind of mixed, but not quite. And the C is combustion. And well, if it's not combustion, it's kind of boring anyway. So anyway, this stratified HCCI, we published some data on it. We did OH and formaldehyde LIF. Basic idea, take 2 cameras, 2 lasers, and get 1 picture of each. And an optical engine, different operating modes. Either you do port fuel injection with extremely low NOx. You add fuel during the compression stroke. You get a factor of 5 or so more. And then if you do it very much later, you get more NOx. So formaldehyde is used to detect things that is warm, and OH to detect things that will be hot. So fuel LIF is kind of cold stuff, formaldehyde warm, and OH hot. So first we did fully homogeneous charge, and these will be the 2 pictures and combined. OH in red and formaldehyde in green, and then you just combine the 2. And then it can look something like this. During the process, the black is this typical 2-stage heat release as you use N-octane. So it starts to burn, then it drops, and then it goes up again. And here you can see the formaldehyde being formed, mainly in this low temperature reaction zone. The formaldehyde drops as the OH increase, and we see that there will be both at the same time. but from the images we can see that they're never in the same place. So you can see formaldehyde being formed, covering pretty much the entire field of view. There are islands without formaldehyde. In those holes the OH is showing up, and then it kind of starts to dominate the process. Again, not homogeneous combustion. So this is a port field inacted, and this is just the formaldehyde surface. So we calculate how much of the field of view is covered by formaldehyde, and we see it's all of it. From here to here, the entire field of view is covered with formaldehyde, and then it starts to disappear. So that means if we would say, let's say at 7 degrees before, if the entire field of view is covered with formaldehyde, it is a homogeneous mixture. A good indication of HCCI, right? We can do the same, okay, the number of cycles again, just telling you that it's not the same from cycle to cycle. Yep, okay, now is a direct injection, and the upper one is pretty much the same as you saw before, port field injection, and that can be compared to the direct injection. Here you can see the fuel injected at, I think it was -50, so at 47 you can see it. And then here you start to see it's not the homogeneous formaldehyde distribution anymore, and then you can see the OH kicking in. And this is the unibus with the second injection here, and that's even a less homogeneous signal. Okay, so this is injecting at -80, and again, it's fairly homogeneous here at -7, but not quite, and then the OH kicking in. At -30, you can see the 5 individual sprays, and yeah, it's less homogeneous for sure. You might also see that the OH signal is a little bit brighter, so there is more OH indicating a hotter combustion. Right, unibus, let's skip that. So what's this? This is formaldehyde measurements at 7 degrees before TDC. So it's the same crank angle position for measurement. And what's then the number up here? That is when we injected the fuel. So if we injected at 300, 200, 100 before, it's pretty much formaldehyde all over the place. So doesn't really matter when we inject the fuel, it's still homogeneous. It's first here at 70, 60, we start to see some holes, and here from 60 to 40, really things happening. And it means that here we started to get a significant stratification effect. And yeah, that means that if we look at the formaldehyde number, this is really 100%, a small drop here, and then the dramatic shift in homogeneity, and it correlates very well with when the NOx kicks in. So if we inject at 60 degrees or earlier, it's homogeneous enough not to form hot zones forming NOx. If we inject late, there will be stoichiometric zones forming NOx. Okay, that's kind of the same story. PPC again, yeah, diesel HCCI. The idea now is to do PPC with the diesel fuel. I just told you that's a bad idea, but maybe we should do it anyway, just to make sure it is a bad idea. So what we do is that we take a single-cylinder diesel engine, we take 3 different piston bowls with either 12.4, 14.3, or 17.1 compression ratio, and this C happens to be the standard one. I think this is blown up here. So that's the standard compression ratio piston. This is then a more wide bowl, and this is an even lower compression ratio bowl. And then let's do this with different loads, 8, 12, and 15 bar. Let's adjust inlet pressure, and let's do EDR sweep. And the EDR sweep is done like this. So we add more and more EDR by replacing air with EDR. So that means that the lambda goes from a really high number down to 1, stoichiometric diesel combustion. And that is then in combination with a really high EDR level. So why are we doing that? Well, we're doing it to slow down chemistry. So we want to inject the fuel and then burn. So separate fuel injection from combustion. And we can do that on this right-hand side of the soot pump. We see that with high enough EDR levels, with the low and medium compression ratio, we can get very low soot with really high EDR. So it first increases very much and then it drops. It's not the case with a high compression ratio. Then it just goes up and goes to infinity pretty much. And that's too high. So this is at 8 bar, fairly low load. And this is then including the other emissions. And you can see the soot here, the NOx, unbound hydrocarbon, and CO. So very low soot, very low NOx, but the penalty is not complete combustion. This is with a very low compression ratio, 12.4. It's also with a very low inlet temperature and with extreme amounts of EDR. So this is at 8 bar, and this is to show why we're doing it. Is it visible? Kind of. So the red is fuel injection, the blue is heat release, and green is the resulting pressure trace. And we see that as the number here goes higher from 1, 3, 4, 5, we get more and more EDR. And here we have a very low NOx and soot, but only 92% combustion efficiency. So, good, but some drawbacks. This is just to show the soot-NOx trade-off, and this is the, I was about to say, right-hand side of the soot pump, but it's shown on the left. Why couldn't we do the high compression ratio? Is because we are not getting ignition delay dropping with the high compression ratio. So, dropping, increasing. So with 60% EDR, we see that we have a significant increase in ignition delay, but then it really kicks in with the two low compression ratio pistons. But we do not get the same kick with the high compression ratio, and that disables us to operate on the right-hand side of the soot pump. So this is at 12 bar, kind of the same story. We see that we need to have the lowest compression ratio, the intermediate not good, and this is definitely not good. And kind of the same story here, that we get more and more delay, and we're not having really sufficient delay, but maybe close to good enough with a higher load. And yeah. Then this is as we adjust the inlet pressure, and a higher inlet pressure means more dilution, and it means that it's easier to go on the right-hand side of the soot pump. So really a lot of dilution, that's good. And yeah, well, let's skip that. And this is the high load, and it's 15 bar, so high load is maybe not high, but it's still 75% maybe. And we see we can actually go on the right-hand side of the soot pump by boosting a lot, and that is then giving us some benefits. So here's this emission summary, and you can see it's really, really a tiny area, but you can get low soot, low NOx with the penalty of combustion efficiency. But you're not really able to separate fuel injection from combustion here. So you're doing all this. Why? Well, you can suppress emissions, but you're going to pay a heavy penalty in the fuel economy. Low compression ratio, that means bad thermodynamic efficiency. Low combustion efficiency, you're not burning all the onboard hydrocarbon and CO. Gas exchange efficiency, not great if you're going to have 75% EDR. And you need to go fairly low load. That means mechanical efficiency is quite bad. So this is the high efficiency concept, right? Something is wrong here. Well, the thing being wrong is the fuel. You're really limited if you're going to do diesel fuel to this load range here. And if you swap to gasoline, this is what's happening. All of a sudden, the fuel is designed not to auto-ignite. And that means that you get a lot of time, maybe even too much time. So this dotted line is the fuel injection, and this is the combustion. And is enough with 50% EDR instead of 75-80%. You can bump combustion efficiency to 97 or so from below 90. I will show even higher soon enough. 8 ppm of NOx, that's good enough, and soot 0.2, also quite good. So all of a sudden, everything just kicks in by replacing the conventional diesel fuel with gasoline. So let's do that. And the first we did was in a light-duty engine. And this is a Volvo D5. The number is, well, it's a 5-cylinder. And here we are not doing a single injection. We're doing a triple injection. So we are injecting at -60. If you remember from the optical diagnostics, that's the last time you can inject and still get a homogeneous mixture. So this is kind of a HCCI pulse. This is injection when it's happening. So that's a control and pretty much a diesel injection pulse, if you like. And this is a bridge in between. And by playing with how much you inject and when you inject these three, you can change the heat release. You can make it HCCI fast, you can make it diesel slow, and you can do anything in between. So you can actually change the width of the heat release here by playing around with the fuel injection. You can obviously change when it's going to burn by selecting when you inject the last pulse. So you have a direct handle on combustion phasing. So all of a sudden, here, we can control the shape of the heat release. So we can be thermodynamic engineers. This is not something possible in a SI engine. In a SI engine, you fire the spark and the flame goes, and you can't really control the burn rate in any good way. In the diesel engine, you inject the fuel, and the combustion is, well, it's doing its thing, but it's very hard to control the burn rate directly. HCCI, burn rate is pretty much combustion phasing, and yeah, you can control it, but it's not really where you want to be. You want to have a reasonably slow combustion, and that you cannot achieve with a reasonable, correct combustion phasing. So, you can become a thermodynamic engineer and design the thermodynamic cycle as you like it. So, doing so is 56% thermal efficiency. Combustion was kind of crappy here. It's only 91%, giving us 51 gross indicated, but still. NOx levels, 13 ppm, emission compliant. CO, but hydrocarbon, not very good. No soot, 0.0. So, yeah, this optimum thermodynamic efficiency. We don't want a long tail like this with the diesel combustion or diesel fuel in the PPC. We don't want this really, really spiky thing with gasoline only. We want a reasonable width and height of the heat release. And that gives us the optimum efficiency of the cycle. So that was the car size. Now it's time for the truck size. Same engine as used for the diesel experiments, but let's feed it with some gasoline. In comparison to a conventional diesel engine, it's a fairly narrow spray angle. So you shoot in the fuel, and this umbrella angle really determines when are you going to hit the bowl as you inject the fuel. If you have a narrow angle like this, you're going to hit the bowl even if you inject fairly early. If it's a very wide angle, you have to wait close to TDC until you inject, otherwise you're going to hit outside the bowl. And yeah, we also bumped the swirl number a little bit. The two bowls as used before, intermediate and high compression ratio. I guess the intermediate is now called low compression ratio. And 2 injections instead of 3, well, the system couldn't really handle 3. But 1 at -60 and 1 close to TDC. This -60 wouldn't work with diesel fuel, because if you inject diesel fuel here, it will simply ignite and burn, and that's not very good. So, high compression ratio piston data first, and what I'm going to show is a load sweep at 1300 RPM using the recipe of PPC. That's 50% EDR and lambda 1.5. And low inlet temperature, 308. So this is the load sweep, and this is the fixed inlet temperature, and here's the resulting exhaust temperature, and this is the inlet pressure and exhaust back pressure as set in our system. And as I said, lambda and EDR should be kind of the same at all load points. Okay, let's skip that. So this is then the resulting efficiency, or efficiencies. So if we start with the combustion, it's 99%. So it's an order of magnitude better than HCCI. So only 1% of the fuel being wasted, not being burnt. This is the 57% thermodynamic efficiency with an optimized combustion at intermediate load. And then it's the parasitic losses, meaning the gas exchange and the mechanical losses. And we see that both would be better as we go up in load. So why did we stop at 12? Well, it's because we are running out of ignition delay. We cannot inject all the fuel before it starts to burn. And we are running out of dilution. So time to stop at 12 bar. HCCI, as I showed previously, the graph was up to 6. So it's at least it's a doubling of what could be achieved with HCCI. Right. So this is another way to plot it. So this is a gross indicated efficiency. So it's combustion plus thermodynamic efficiency. And then you added the gas exchange losses and then the friction losses. And we see that the brake efficiency will be 48, 49 or so. And kind of flat. And yeah. This is gas exchange loss analysis. It turned out that we had way too much pumping losses over the inlet valve. Someone forgot to take away the plugging of one of the inlet ports, so there was a lot. Yeah. So this is just another way to explain the different losses. So this is absolute energy losses in bar. So heat losses, friction losses, gas exchange, combustion losses, all with the same unit, so we can directly compare how much does it cost not having complete combustion, how much does it cost to have improper gas exchange, etc., using the same units. And then you can relate it to energy input, and that means it's becoming more of a flat line. At higher loads, of course, you add more fuel. You can do it like this, percent of total with different colors. It's the same data, just different ways to represent it. Emissions, well, the horizontal line is Euro 6, US 10 emission regulation, and we see that we're below that in terms of NOx at all operating points, and that's because this happens to be the set point. And at 12 bar, we're not emission compliant, so we gave up. Unburned hydrocarbon, slightly above the legal limit, but we're below 1 gram of unburned hydrocarbon, so that's very low for any gasoline engine. Soot at low load, not a problem, and here it's not so good. CO below legal limit at intermediate loads, and at low loads it goes really high. We are running out of temperature, so combustion is not complete anymore, and that's not good. So why is 55 better than 57? It's because as we reduce compression ratio a little bit, we lose in thermodynamic efficiency, but it also enables us to go higher load, because lower compression ratio means a little bit less temperature, and that means we can go to 18 bar instead of the 12 bar. And that enables us to get a higher efficiency, as the parasitic losses will be less dominant at high load. Combustion efficiency is 99.9, and that's much better than before. It's actually an order of magnitude improved again. So HCCI was 90, the high compression ratio piston 99, and now it's 99.9. So that means unburned hydrocarbon and CO below legal limit without after treatment. There is no bump here at 257 at the intermediate load with the lower compression ratio, but we can maintain 55 all the way from low to high load. So that's good. And yeah, so this is just a summary in different ways. So this is gross indicated, net, and the brake. And we see that we're approaching the 50% point with the brake efficiency. And again, some exercises with different losses, absolute numbers relative to energy input, and colorful graph showing the sum being 100%. Can be used for a more detailed analysis of the results. I'm pretty sure you don't want that. Emissions, well, again, hitting the legal limit at 18 bar, and below that, no problem really with NOx. Unburned hydrocarbon creeping down below the legal limit, CO well below legal limit. Soot is a factor of 4 less than previously, but maybe not good enough anyway, so 1 FSM. All this data would be with one specific fuel, and we could then change the fuel and see what's happening. So let's do that. Let's find some different fuels from Chevron, and these will be the numbers, 47330 to 8. I think few of them are lacking in the matrix, but we did run them as well. So they're ranging all the way from 99 to 69 in RON, from a very small difference between RON and MON to a high one, and we also thrown in ethanol in the mix. So why testing such a wide range of fuels? Can the system handle this fluctuation? Is there a preferred fuel, or doesn't really matter? So for all the different fuels, we ran pretty much the same conditions except ethanol in terms of inlet temperature. Same boost pressure, same EDR level down to the 5 bar point. At the 5 bar point, we dropped EDR and went lean burn instead. And we see that here fuel actually would have different appetite. We also changed injection strategy quite a lot when changing fuel. So there were 2 fuel injections. First, close to 60 and one close to TDC. We can see that ethanol, for instance, pretty much all the fuel goes 60 degrees before, and a very small amount, actually here at low load, none, but then a small amount at higher loads. Other fuels would have no fuel at all in the pilot or early. All the fuel would actually go in the second pulse. And this is to adjust the combustion appetite for octane, or should I say the opposite, how to adjust the thermodynamic cycle based on engine octane, a fuel octane number. But if we do it right, we get pretty much the same thermodynamic efficiency, plus minus a % or so, with this re-optimization of the process. If we would not re-optimize, this would be all over the place with really bad excursions. Oops, like this one. That didn't go very well because it's not a fully optimized point. So this is thermodynamic. I said 55 before for one fuel, and you can see it's from 56 to 54 pretty much all the data points. So the fuel I picked previously is in the center of the bunch here. Same thing with the combustion efficiency. We see that at the higher loads, we can maintain above 99% combustion efficiency. So it works, and you can get the numbers with all the fuels, meaning the high efficiency numbers. Emissions, this looks like a total scatter, like this one here. That's because we said as long as below 0.3, who cares? So there is no longer a minimization of NOx at the lower loads. Just make sure it's below 0.3. CO, kind of the same with some excursions. Unbound hydrocarbon, well, ethanol, really high, low load, not a good idea. And soot, there is kind of a large scatter from gasoline to gasoline, but ethanol, of course, being the king. With ethanol, there is no particulates. So you could say that ethanol would be emission compliant with all four without after-treatment. So that's good. Okay, the final one, how to reach full load. Let's swap hardware to a D13 instead of a D12. The number implies that it's slightly larger displacement, but most important, it's a modern machine with a modern fuel injection system. It's also with a different combustion chamber shape and a different spray angle. It's not really optimized for HCCI or PPC, but more classical diesel. But even so, we did some experiments, and we were up to 26 bar IMAP, and as you can see, we're hitting 50 brake. So less difference from gross to net to brake with this more modern engine, with better gas exchange, with a better injection system, and so on and so forth. So this is the intermediate. So combustion efficiency 99.9 as before, and the parasitic losses much less dominant with this modern machine. So actually the thermodynamic is not improved compared to the older one. So this is a load sweep, or actually 5 different loads, just to illustrate how things change as you go from a low to a high load. And I'm not going to show each and every one here. I'm going to show one at a time. So this is a 5 bar, meaning low load. The red is fuel injection, the blue is heat release, and the resulting pressure trace in green. From here and onwards, it's actually no fuel injected, it's just a signal. So fuel stops here, and then combustion starts here. So quite a long ignition delay, and it's quite a homogeneous combustion, more close to HCCI than diesel. Low NOx, 0.1, and very low soot, and efficiency should be, well, it's only the combustion efficiency, but it's good. And then as we go from 5 to 11, like this, we see that separation between fuel injection and combustion would be less, but still it's quite good. And this is then 16, and now we are seeing that they are getting a bit close. Still, emissions are under control, and combustion efficiency is now kicking in, like 99.8. 20, now the heat release shape is a little bit different. It's more like a square profile, not this Gaussian shape. And the separation is maybe there, but not much. There is another thing you can note here, that the green is now hitting 200 bar. That's the peak pressure. And Scania, the engine manufacturers, told us, oh, well, stay below 200 bar and do not blow up the engine again. So, of course, we did not. So that's why the published data is also 200 bar at the 26 bar load point. But in order to achieve this 200 bar, we have to retard combustion, move it late. And moving it late means that we're going to lose in efficiency, and it's not as good of a point, this 26 bar, as the 20. But being able to go high load means quite a lot in terms of, well, engine performance, normalization with peak power, etc., etc. So load is important. So this small retardation here is worth it in order to go up in load. Yeah, this is just to show that the noise is okay and combustion stability is okay. Emissions, again, the horizontal lines, emission compliant, Europe and US, and we see that, yeah, it is. We're below with unburned hydrocarbon from 15 to 26 bar. Same thing with the CO, and we're now at 0.25 in soot. So it's a factor of 4 improvement again with a more modern injection system. Now we're approaching legal limit in terms of soot with gasoline fuel. Let's try some fuels in this more modern geometry. Same fuels as before. They're now grouped in high, medium, low octane. And we also got hold of some isoctane and octane mixture and some diesel. This is diesel class 1 in Sweden. We did not do the ethanol at this time. And this is showing the operating range with the different fuels. The red is then the diesel fuel, and I'm showing here that you can run the diesel engine on diesel fuel. Yep, okay, good. But you can actually do the same with low octane gasoline. So you can go from the lowest to the highest loads with 70 octane gasoline. Not so easy to do that with the racing fuel, meaning like 99 octane gasoline. Then the minimum load is like 15 bar, which is a little bit inconvenient. You can always say to the police that, sorry, I couldn't go low load. I couldn't really reduce engine power, so I had to go really fast. It's not going to work. So it would be convenient to be able to go low power, low load, also with high octane fuels. And that's, I think, the last part of my talk, how to go down with low load with too high octane number. But before that, well, this is just a summary of all the data points with different gasolines, and it's showing efficiency versus NOx, and it's kind of in the box, or at least soot NOx is in the box, so it's good enough. This is the 5T diagram. Finally, I showed it, right? So this is equivalence ratio temperature. This is where you want to burn. Don't burn here, because then you form soot. Don't burn here, you form NOx. Don't burn, or, well, don't do partial burn here, because then you get CO, unburned hydrocarbon. So burn in the box, and the box can actually be plotted like this, but it's kind of hard to see. It says temperature and EDR ratio, and it's different lambdas, so I think it's blown up like this. And there are two horizontal lines. Anyone, supposed to be horizontal, anyone remembering the 3 temperatures of HCCI? So temperature 1, 1000, that's because that's when we start to burn, right? It needs to be 1500 because CO want to go to CO2, or we want it at least. And we should stay away from thermal NOx production, and that's 2000 Kelvin, right? So what's plotted here, that's 1500, that's 2000. So here it kind of gives us where can we do different combos of EDR and equivalence ratio, or lambda. And if we take this one, that's 1.5, and we take 50% EDR, we're kind of in the center of the box. So that's why using this recipe for PPC would give you a good combustion efficiency because it's high enough temperature to burn off the CO to CO2, and it's low enough temperature to stay away from thermal NOx. And of course, it's not one digit. It's a distribution in the chamber, and you should make sure that each and every element of fuel would not go below or above these limits. Okay, soot. Swapping from diesel fuel to gasoline, you get an order of magnitude in soot, roughly. Different gasolines give you an order of magnitude difference in soot. Why? Actually, I don't know. It's a little bit complex, I think. That's a normal answer if you don't know. But there is a dramatic change as you go from diesel fuel to the lighter molecules. PPC and fuel efficiency, should I do that? Yeah, sure, let's do it quick. Let's optimize efficiency. And how should we do that? Well, first, you need dilution. You need to burn fast, and you need to burn complete. Then you get efficiency. And dilution, well, this is the efficiency, gross indicated efficiency as a function of inlet pressure and the amount of fuel you add. So if you say you add 30 bar of fuel map, as you increase inlet pressure, efficiency increase. So going like a vertical line like this. And the numbers from 48 to 52, this will be a simple thermodynamic analysis, kind of pen and paper type of analysis, but of course done in MATLAB. So that seems to be the way to do it. Add more dilution. Why? Well, if we look at it, it's mainly the heat transfer losses dropping. Because adding more dilution means less temperature after combustion. And that gives you less heat losses. Not so much difference in exhaust losses. Is that true? Well, let's do inlet pressure sweep, same Scania as before, the D12. And sure enough, so this is low inlet pressure, this is a high inlet pressure, and we go from 45 to 55% indicated efficiency. So from kind of boring results to really interesting, world-leading results by simply adding more dilution. The numbers again, different fuels, and yeah, slightly different response, but not much. Why? Again, heat transfer losses really dropping, exhaust losses dropping at first, but then kind of staying the same. Why bumping up here is because this is close to stoichiometric combustion. So that's using additional EDR. That's additional air. How about using additional EDR? Same story pretty much. If we have a certain amount of fuel, certain amount of air, and just add an additional component, that's EDR, what's going to happen with efficiency? Well, this is how you do it. You increase by adding higher and higher inlet pressure. So the partial pressure of fuel and air is the same, and then you add a partial pressure of exhaust. keeping lambda constant. And what's going to happen? Yeah, pretty much the same story from 51 to 56. So again, from kind of lukewarm results to really good results by simply adding more dilution. So, of course, there are people doing extrapolations saying that, at what EDR level will we have 100% efficiency? It's not very easy, right? Is it? It's hard to get more than 100%. Okay, so why? Same story again, heat transfer losses dropping, some exhaust losses as well, but not as much. And yeah, you have some side effects, NOx dropping in order of magnitude and soot going up, and combustion efficiency drop if you go too much, EGR. Okay, high dilution, reduce heat transfer losses. That's really the conclusion. Fast burn, same back of the envelope type of calculations again. And these would be the exhaust loss and heat transfer loss was on the axis. This is when would we burn, and this is how fast would we burn. So if we burn really fast, really early, there is not much energy going to the exhaust. So that's good. Burning late and slow is a bad recipe for having low exhaust losses, but it's really good for heat transfer. So it's quite obvious that if we minimize one, like putting here, then we maximize the other one. And we're not really interested in minimizing or maximizing these guys. We're interested in maximizing efficiency, right? And the efficiency would be the rest, so that's kind of this one, telling us that we should have a combustion phasing around 5 degrees after. It should be burning reasonably fast, and of course the optima is here with extremely fast, but it's a very flat optima. So as long as combustion is like 10-15 degrees crank angle, it's fast enough. So that was back of the envelope calculations, and of course they're correct, but should we verify maybe? So this is indicated efficiency, this is combustion phasing, and again it shows that if we burn early, we get 56% or so efficiency, good. If we burn late, we get like 46, bad. So a dramatic change in efficiency. We cannot afford to burn too late in the cycle because that would give a poor efficiency. Mainly because of exhaust losses. We're pumping the energy to the exhaust and not on the piston. And there is a slight problem though. If you burn really fast, really early, you get a lot of pressure rise rate, and that generates a lot of noise. So if you want the highest possible efficiency, you also have to accept that the engine is noisy. Scania is saying the sound of economy. So a quiet engine is a bad engine. It's not efficient. Okay, NOx and soot, let's skip that. Complete combustion, yeah, burn the fuel. Make sure that combustion efficiency is at least above 99%, otherwise it's going to go bad. So HCCI is actually not a good concept in that way. Yeah, too low load with too high octane number was that. Yeah, before that, let's do the summary if we don't have time to finish the rest. So this would be the 3 different campaigns I've been showing results from. The D12 with a high compression ratio, low compression ratio, and then the D13 with the standard compression ratio. And this will be the brake efficiency. So this is the one giving 57 indicated, this is giving 55 indicated, and this is only giving something like 54 indicated. So that's why I was saying that 55 indicated is actually better, because counting all the parasitic losses, you actually get a higher brake efficiency. And no one cares about the indicated. It's all about the total system. That will be of importance. So emissions, yeah, kind of the same in terms of NOx. This is different optimization, the D13. Here you can see it looks dramatic from 4 to 1 to 0.25 in SUT. And maybe it is, but it's mainly due to the injection system. And unbound hydrocarbon, it's gas emission compliant here, not so with the old one. And here you can see also dramatic reduction with the new injection system. Okay, yeah, there is also a little bit of a problem. We want really high dilution to get this really high efficiency. That means that we want a really high inlet pressure. And at the same time, we're burning a lean charge with not very high exhaust temperature, and hence exhaust enthalpy. And that means that we're looking for a turbocharger that is giving us really high boost with no exhaust energy to work with. So this magical turbo would be really nice to have, but in reality, it's not quite there yet. So this is what we need in terms of turbo to achieve the numbers as shown from the single cylinder. They are still realistic, so below 50% turbo efficiency. So it's okay, it's doable, but it's not an easy task to get these numbers. Yeah, so this is the D13. This is gasoline, this is diesel, and quite a good improvement, I guess. So the summary before doing the Limbo. Should use gasoline instead of diesel. It's the most efficient of all processes known in terms of thermodynamic efficiency, 57, combustion efficiency, 99.8, very reasonable gas exchange and mechanical losses. Load range, high enough. Well, we actually did 30, but we broke the engine, so data is not published. And low enough emissions. So, the Limbo project. You know how to dance Limbo? Anyone? I don't ask you to do it, but you know how to do it? Well, you have a bar, and then you should walk under the bar, right? It's easy if that is 2 meters high, but it's less easy if it's 1 meter, or less and less and less. So this is kind of the same thing. How low of a load can we go with too high of an octane number? So what's the minimum load with a less suitable operation? The correct answer is do not swap to gasoline, from gasoline to diesel, and then everything is easy. But if we cannot do that, how should we go about to do it? So it's this point here. How can we go down to this point here? And so let's do that. What can we do? Well, we can do injection strategies, split, we can trap hot residuals, like the controlled auto-ignition. We can use a glow plug, and so on. So this is a Volvo D5. It's a light-duty engine. We operated with an active valve train, like this one here. So we can open and close the valves as we like from the computer. And that enabled strange and interesting operating schemes. Okay, this is the fuels, 87 octane gasoline, and this is the valve operating points. So we see that if we close the exhaust valve way early, we have a lot of recompression and re-expansion. And then if we inject the fuel here, we actually convert the gasoline to diesel. Make it a lot more reactive. We can inject a little bit here, a little bit here. The interesting thing is that if you inject every cycle, and you get a little bit of heat release every cycle, is this a 4-stroke engine, or is it a 2-stroke engine? It's only doing gas exchange every other revolution, but you have combustion every revolution. 3-stroke? I'm not sure. Anyway, so this is how we did it, changing this NVO, negative overlap, and by that adjusting how much recompression we get. There's another way to do it, and that is to open the exhaust valve again. So you have the exhaust valve open, you close, and then you open again, and the exhaust and inlet will be open at the same time. That means that you're going to suck back some of the exhaust during this process. It's called rebreathing, this concept. So the combustion stability, we're comparing rebreathing and MVO. So what's on the axis? This is kind of the amount of additional dilution or trapped hot gas on the x-axis. So this is a rebreathing crank angle, and this is NVO crank angle. It's not starting and stopping at the same crank angles, but it's kind of adjusted. And on the y-axis is the load, and we want to go as low as possible down in IMAP. And we see that as we add rebreathing, this good area here with less combustion fluctuations, it goes to lower loads. Same thing with MVO, that here seems to be a good spot for combustion stability. So both works very well. This is unbound hydrocarbon. Which one is best? Kind of similar improvement, I guess, or maybe not improvement, but they're not getting very bad, at least. Okay, well, actually, it is a bit of an improvement. If you keep load and just add MVO, you see that you actually reduce unbound hydrocarbon. Here's then the killer. Rebreathing, the gas exchange efficiency is very much better than if you do MVO. Here we're dropping like 10 or more percent points with the MVO. And it's not actually flow losses during gas exchange. It's actually heat losses during the recompression, re-expansion. Temperature is very much higher, and heat transfer to the walls would increase. Okay, and that means the net indicated efficiency, rebreathing, better, MVO, so-so. And this is then injection at the wrong TDC, and let's do that and see what's going to happen. And so we inject and we release some heat. So combustion at the wrong TDC. So this is a different one with different setting, but still. You have to be careful so there is enough oxygen. So if you add too much fuel, there is not enough oxygen left. You're going to go really rich and generate a lot of soot in this combustion. And yeah, so this is the ignition delay from the main combustion as we add fuel in the wrong TDC. And we see that the ignition delay gets less here as we have a lot of MVO, meaning hot residuals, a lot of recompression, and yeah, add fuel there. Combustion stability, yeah, it's improved down there, and unbound hydrocarbon is improved, good, and NOx, oops, a lot of NOx here all of a sudden. Why? Well, it's now a stoichiometric mixture in the MVO, and that's a good recipe for NOx. And the soot, in this region here, we are adding too much fuel. We go rich at the MVO, and that's also very bad. Yeah, this is the lambda, this is the soot and NOx, and here you can see that it's actually kind of rich, stoichiometric here, and then actually rich over there in the corner when you generate soot. Okay, enough of that, putting it all together. What should we pick? That really depends on the load, because if you look at stability, this is the best. This is NVO with the maximum amount of MVO, so that's the best. But is it always the best? Well, if we look at here, this is this that was the best. but it's now generating 1 FSN of soot instead. Oops. So can't really be used here at the higher loads, but here in the very low loads, it seems to be the best one. In efficiency-wise, rebreathing is good, but we can't go as load down. So we're not dancing as good of a limbo. Here we need to do these ones, but we then pay the penalty in efficiency. So do MVO here, do rebreathing here, and then we're good. So I think that's kind of it. This is the first slide I showed you, the different combustion concepts. I gave you a little bit of HCCI information, not so much here, but maybe a little bit here as well, the PPC. As I said, this is the short version of the talk. There is a longer one. That is also taking the next step from PPC to the really high efficiency thermodynamics. But I guess we have to save that for next time. This is a modified version of the bubble graph with a timeline saying that once upon a time we had SI, moving to HCCI, then diesel PPC, and then gasoline PPC. And yeah, that's it. Thank you.
I'll take the privilege of asking the first question, Bengt.
Sure.
First, thank you.
Well, you have the mic, so.
Yeah, exactly. And question is, you know, there's lots of buzz I hear in the last few days about how Europe is banning the diesel. Mm-hmm. How does that affect what we do?
Well, I also heard that they might also ban the gasoline engine for the same reason. That there's a big difference between real-world driving emissions and certification emission levels. My opinion is that it's mainly due to sloppy legislation. There actually were no laws, no rules, what could a vehicle emit during real driving. The only law would be that you take the vehicle, you drive the test cycle. If that is low enough, okay, certified, and that's it. Any other speed load operating point would be not controlled. So then you have to ask, would any OEM add emission system cleaning up the exhaust for an additional 2,000, 3,000 euros a car? There is no law. Is the customer asking for it? Not really. Why would you? In Sweden, I make kind of an analogy to, do you want to pay more tax just because you think it's nice? Or you're just paying according to the rules? The same thing with the OEMs. They follow the rules, and if the rules are not really correct, then... Yeah. Okay, we have a question.
Okay, thank you. First of all, thank you for showing all the different plans maybe for the future and all the schemes. I have noticed one engine proposed, and I believe it might be available in the market. It's a variable compression turbo. I may say the name of the manufacturer.
You mean the Nissan one? Or?
It's an Infinity, Nissan Infinity, yeah.
Yep.
Also, it's a gasoline engine, right? How does that, is that somehow related to, because I saw the SAB engine where you have to modify the cylinder head or the block?
Yeah, it was kind of the same as the Saab, with the same idea. Let's see, it's a few slides up. Yeah, here somewhere. That one. So this engine came about as having the same concept as the Nissan Infinity. going a really low compression ratio at high load, and then for enabling really high BMAP in SI, and then at part load increase compression ratio for efficiency. And it was designed for, I think, 7:1 up to 14:1 compression ratio. When we converted it to HCCI, we went 10 to 30, so 30 compression ratio, but that's really something you adjust when there is that much of a stroke in the variable system.
So is the market going that direction? Is it going to be like the first, and that will other companies will follow after that one?
I think Saab was kind of in the right time to release it, because at the time you could go really high load in SI without paying too much of a penalty. But today you have the real world driving emissions. You cannot enrich at full load anymore. You need to go stoichiometric, otherwise you're not emission compliant. And I'm not sure that doing 7:8:1 compression ratio would be emission compliant with conventional gasoline. A variable compression ratio is really good, but maybe not for conventional SI. And yeah, I did ask Nissan to get one here.
You showed many ideas for getting low emissions, and you saw indicated or even delivered efficiency on the order of 50-something%. Oh, can you hear me now?
Yep.
Ah, perfect. So you showed low emissions and getting towards efficiencies of 50%. My question is, when you think of the ultimate, what do you see in the size range, the highest efficiency you could imagine with whatever technology you would want to put in?
I only had 4 hours, so I skipped the last hour. It's called the high efficiency thermodynamics, and my goal is 60% brake. But that's more thermodynamics and not so much combustion. I think this is a combustion summer school thing, so yeah. You need to work more with the thermodynamics to get it right. You need to go in the range of 60:1 compression ratio to get these numbers. Can you do 60:1? I think so, but not in a single stage. 60% is a good even number. I've seen Nissan indicating that their goal is the same. Mazda said the same, and I think it was Honda or Toyota, I can't remember, but the other guys. So they're all aiming at 60. So is Cummins for a heavy duty, as well as Volvo Trucks. So I'm quite confident we're going to see that number in reasonable time frame. It's not going to beat the gas turbine, though, right?
We have a question from Facebook, from Alper Jonter. It says, Dear Professor Johansson, thanks for the lectures. I would like to learn your views about RCCI engines in comparison to HCCI engines and PPCs. Which one do you think will be more useful for commercial vehicles in the coming years?
RCCI is a version of HCCI. It's a way of controlling the HCCI with all its benefits and drawbacks. You can get extremely low NOx and soot, but you still have the control issues with the closed loop combustion control and so on. PPC can be kind of a modified diesel engine, so it's much easier to get a stable operation of the engine, but with a little bit less emission advantage. So which one would be best, hitting production the most? Well, PPC is there. It's part of the calibration of diesel engines today. If you say that the definition is that the fuel is in before combustion starts, All light-duty diesels today, below 20 to 25% load, they will be PPC today. But it's getting up in the load, getting up in the efficiency, then you need to swap to gasoline. And I don't see any diesel engines running gasoline. Well, actually, it's not quite true. I'm told that something like 100,000 persons a year is filling up their diesel cars with gasoline anyway, because it's possible. So it's a small nozzle into a big hole, and yeah, you can. So apparently it's happening quite frequently. That number is from UK only. But you shouldn't without knowing what you're doing.
Hi, I actually have 3 questions, if that's okay.
Yeah, sure.
First one is, what's your opinion of the new Mazda so-called HCCI engine that's coming out? Second question is, what was your view of combining either HCCI, RCCI or PPC with a hybrid powertrain, maybe the engine never actually driving the wheels, only there for charging? That would seem a way of addressing some of the load and operational problems of the idea. And also the results that you've shown in the latter part, you were going up to 26 bar IMEP. You were running some, what I think probably some quite high inlet pressures, and then you did mention the turbo. I'm assuming you were getting those pressures from a supercharger, not a turbo, and was that driven from crank or from a motor? In which case, if it wasn't off the crank, were you including that in the efficiency calculations?
Okay, so 3 different questions. Of course, I forgot the first 2 already, so let's start with the last one. When we did the experiments, it was single-cylinder operation, and that means you set the pressure, temperature, you feed to the engine, and you also adjust the exhaust back pressure. And you do that in a way so you get a realistic condition based on a certain turbo efficiency. So based on the exhaust enthalpy, you can calculate what would be the power you can deliver to a compressor from a turbine, and then with a compressor efficiency, what pressure can be delivered. So this analysis of the gas exchange is done, should I say, in a virtual way. You only get the real results if you do a multi-cylinder and with the correct turbocharger matching and everything. So that needs to be done. You can't only do single cylinder, because then all of a sudden you have 10 bar boost and no back pressure, as I said, and that's really good for efficiency, but it's totally unrealistic. So you need to be able to match, and I think, well, of course I did a little bit too fast in the data, but let me show. So this is the conditions. Where did it go? So this is the inlet temperature. This is the inlet pressure. And then you can see that the exhaust pressure is slightly higher than the inlet pressure. And that is in order to get the, well, a realistic turbocharger efficiency needed to get these points. These are actually for the low load, and I think actually yeah. So here you can see that the exhaust back pressure is a little bit higher in comparison to inlet pressure, because here we assume that the turbo is not as efficient as well as up here. So you need to take that into account, otherwise you can get any kind of numbers. So that was your last question. The intermediate one, how about combining HCCI with hybrid? Right? No. That's a bad idea, because HCCI is a part load efficiency concept. And I think I can show that by repeating one of the efficiency slides. Let's see where that is. So, or actually maybe this one, is showing that we're stopping at 4-5 bar BMAP, and we see that the conventional engine is kind of, it's not too bad as we go up in load, and it's actually, I should have included more slides apparently, but if you summarize all this, you're going to see that the conventional engine is not too bad as you approach 5-6 bar, and if you then go to 10 bar, it's actually on par with the HCCI. So a hybrid is normally operating at the best possible point, and that will mean 10 bar for the SI, and that also means a fairly good power density. So you need to beat it in absolute best brake efficiency, and it's not so easy to do.
My thinking partially around the combination was more dealing with some of the transient issues of HCCI.
No, transient is not a problem. We did a full transient test cycle with the VCR HCCI, and yeah, it works. If you know what you're doing in terms of closed loop combustion control, you have a good enough predictive model, especially the wall model needs to be there, because the wall change behavior in the time constant of roughly a second, and that's maybe 10, 15 combustion cycles depending on speed. So the first 10 or so cycles are totally different from the steady state. If you have that in your dynamic model, it's not too hard actually to do this. There are plenty of milliseconds from combustion to combustion.
And the final one was your opinion on Mazda's.
Yeah, right. That I forgot, of course. Mazda SkyActiv X, as I understand it, is pretty much spark-assisted compression ignition, but with a significant difference. They do fuel injection fairly late and put more fuel next to the spark plug. So it means that the flame propagation is doing its thing with a fairly rich mixture. So that's stable enough then. And the HCCI is then happening with a fairly dilute, and hence not burning too violent. So it's normally a very small window of operation where you can get spark or flame as well as not violent HCCI, but with this additional fuel injection, it might be good enough. But they're starting with a fairly good concept. They have 14:1 compression ratio already with the SI engine. So
Bring in their diesel compression ratios and gasoline compression ratios together at Mazda.
yeah, it's 14:1 in both cases for Mazda, and it's been so for 10 years maybe, at least 8. So well, 14:1 happens to be the best possible if you have a half a liter displacement cylinder. If you go well above 14, then surface area is starting to increase, and you're starting to get more losses, and the thermodynamics is not really helping you enough.
He asked my question in his second question.
Hi, thank you for your presentation. So I kind of have a fun question. So given all of your experience, what do you think engines of the future would look like?
I think they're going to be much smaller. They're going to be fully optimized for efficiency. They most likely are going to operate stoichiometric with high efficiency anyway. Why stoichiometric is because the freeway catalyst is extremely effective, meaning you're down well below zero emissions. Why smaller is because, well, the power density is going up, but I see very few vehicles without a hybrid. There is no reason not to have a hybrid, except for cost, obviously. But with a hybrid, you decouple the engine operation from the vehicle need. So you deliver enough energy to the system, and you do that always with best possible efficiency. A Toyota Prius is never below 34% brake efficiency. It quickly goes up to 38, and then it's around 40 in most of the operating points. And that's the baseline today. I see in Hyundai saying 42.2 to 43% for the next year model. Gasoline, hybrid machines. So that's the baseline we're talking about today. And then we need to improve upon that to get to the next level. And as I said earlier, my own goal is 60% brake efficiency. That also means that we are only 20 percentage points less than all battery electric powertrain. People think that's 100%, but it's not really. It's more in the range of 80% if you calculate energy loss when charging the battery, releasing the energy from the battery or the power electronics in and out, and the electric motor that is not always operating in the best operating point. I think a Tesla S is more like 70% efficient, the electric motor. So it's not very good, actually. And yeah, there's another a significant benefit, if you're not here, but let's say in Sweden. It's quite often quite cold. And if you have 60% efficiency, the other 40% can be used for heating the car. And that means that the efficiency offset compared to a battery electric vehicle is very minor. I do have another presentation. It's called The 6 Reasons Not to Buy a Tesla. But maybe that's for some other time.